Hello, in this course I will teach you about Big Data and NoSQL. We have a set of exciting topics. First, we will start with introduction into Big Data. We are going to see the key algorithms for processing large volumes of data. This is the MapReduce algorithm and Hadoop project. HDFS, Hadoop Distributed File System, is the foundation that enables us to reliably store large volumes of data. We will then see the Hadoop infrastructure, and then three very different ways to program Hadoop: Hive, Pig, and Scalding. Hadoop has a growing ecosystem, and we will explore key elements of it. After that, we are going to see the area of NoSQL, non-relational databases, its key categories and characteristics. Streaming is our next section, in which we are processing data in real time, and we will finish on how to introduce Big Data and Hadoop in the enterprise. In this section, we will talk about some challenges related to big data. One thing that you will see in almost every presentation about big data is that we are facing an unstoppable information growth. The amount of data that we are handling is rapidly increasing. So if we illustrate the growth of data, we will see that we have a tremendous growth, and we are actually just at the beginning of the curve that is going really straight up. When we look into the big data sources, we want to see what are the key sources for this big data. Traditionally, we have our business transactions. Various business systems are generating data, and we have more and more of this data. But it is interesting that this part is relatively well understood. We have our relational systems that quite successfully handle this area, but there are some associated forces with that. One of the big changes in this space are the social media. We have Facebook and blogs and Twitter, and the users are generating tremendous amounts of data. Now, this data, as you will see later, cannot be really successfully stored in relational systems. And this area was actually very important when it comes to introduction in new data stores which can handle this amount of data. In addition to this, we have arrays of unstructured data. So we have a tremendous amount of text that is generated, text that we would like to analyze. We would also like to understand what is this text about. Increasingly, we have other non-structured data like images and video. And imagine you would like to be able to make queries about who is in some video. So conventional systems really don't have good support for dealing with this type of data sources. Sensors are one of the most exciting new sources for big data. Sensors can generate tremendous amount of data that we need to store and process, and it is likely that sensors are going to be the most interesting new contributor to the growth in big data. Let's talk now about some characteristics of big data. The first characteristic of big data is naturally the volume. The amount of data that companies generate today is really staggering. If you think, for example, about the New York Stock Exchange, it generates about 1 terabyte of data, of trade data, for every trading day. If you look, for example, at Twitter, Twitter generates tens of terabytes of data, and this data can be fed into the sentiment analysis, and based on that, we can discover what people feel about various products or events. Volume is going to be particularly important as we are having our devices that are sending data. For example, power meters are generating billions of readings every year. And imagine we can analyze this data to optimize the energy and actually foresee the demand for power. Velocity is another important characteristic. For various time-sensitive activities, for example, if we are detecting fraud, seconds can be decisive in being successful or not. The other aspect of this velocity is when we try to combine the data that we are getting in real time with the data that we have from before. Another good example is the sensor data that we are getting. For example, in modern cars, you have nearly 100 sensors, and these sensors can generate a very large volume of data arriving in a very rapid pace. Variety is another component. We said that traditionally business generate transactional data, but now with users being on the internet, users generate tremendous amount of data, images, text, videos, and we need to process all of that. And finally, one of the interesting characteristics is veracity. Can we trust the data that we have? And it is interesting, in one poll of the various business leaders, they stated that about 1/3 of them actually does not trust the data that they have in their organization. So determining if some data is truthful is a very important challenge for big data. Big data workflow. It is not enough just to store and process the data that we are getting. We actually need to include this data into a bigger picture that we have in our enterprise. So the first thing that we need to do is, of course, to acquire the data. This acquisition can happen in various ways. Sometimes the data will arrive in a batch mode. For example, when we get large files that contain, let's say, sales records and similar. Sometimes the data will be coming as a stream. For example, when we have various sensors that are generating data, or if you are collecting Twitter data that is coming in real time. We need to store this data. And it is interesting that traditional databases do not provide a good answer for storing this data. So we will see later different mechanisms and approaches that have been developed to store this data. The principal idea there is that the data will not be stored on one machine only, but the data will be spread in a fault-tolerant and reliable way across many machines. And that poses challenges. The next step is analytics. We will be applying various mechanisms. Sometimes these are going to be queries in a way similar to what we do in conventional systems. Sometimes we will apply data mining, sometimes machine learning, and we have quite a bit of options how to try to figure out useful information in our dataset. When we get this information, we need to present it in such a way so that somebody can act on it. Visualization is one of the key aspects there. Showing just numbers is usually not enough for most humans, so we need to have some visual, easy representation so we recognize the trends, recognize significant events, and recognize when should we act. The next thing in our workflow is the management of data. You need to figure out not only how to put this data on your systems and how to process it, but also what is the structure of this data. How are you going to integrate it with conventional systems in your organization? Who will have access to this data? How are you going to manage the users of this data? How are you going to approach security and similar? The data that we collect needs to be shared. And sharing of this data is a particular problem because we are dealing with staggering amounts of data. So you cannot just put it in an email attachment and send it to somebody. We are dealing with such volumes of data that impose a challenge. Sometimes you will find that it is optimal way to use a fast network connection. In some cases, it is surprising, but FedExing hard drive or set of hard drives with data can be actually faster. And finally, we got to the point of integration. It is extremely important for your success in big data that you always integrate your conventional systems with your big data systems. Conventional systems are still the cornerstone of modern business, and they have many activities that are truly best suitable for this type of systems. How do we combine the big data and traditional data processing is a very important subject, and you must cover the topic of integration very early in your enterprise. Talking about this whole workflow, the key thing for us is that the business needs to see a value from the big data chain. It should not be just viewed as a technical exercise. It really needs to contribute to higher revenues and some benefit of the business. And we need to execute all of that elements of the workflow in a cost-effective manner and in a reasonable amount of time. Let's see now what are some problems in capitalizing on big data. First, we have more data than we are used to. What that means is that you don't need to have necessarily petabytes in order to have a big data problem. If you have more data than your organization is used to, you are dealing with some type of a big data problem. And what is interesting here is that the volume of data there is not necessarily extremely high. You may be dealing with not so high volumes that still can present a challenge. The other problem that we have with modern big data systems is that produce data that does not fit naturally into conventional data stores. So we have already seen that we have various types of unstructured data formats like images, videos, and text, and they're really poor match. So organizations are often puzzled how to deal with this type of information. The other issue that organizations have is that the data arrives quickly, and that also means that the usefulness of this information is limited. For example, if you are looking for a fraudulent transaction, you may have a very limited time in order to react and intervene. This also poses challenge to organizations that are already using some form of big data, because traditional data systems, typically those based on Hadoop, are oriented towards processing of data in batch mode. When we deal with real-time data, we have difficulties with systems like that. Then, even if you have a lot of data and if you manage to store all this data, the problem is that it is not really clear what you want to analyze. How are you going to get benefits from this data? What would be the right mathematical models to apply? What kind of mining and analytics approaches should we apply? And the knowledge for figuring this out is relatively scarce. One of the things that is really critical in dealing with big data is to remember that big data systems are not isolated islands. You always need to integrate these big data systems with conventional systems. Their information flow needs to be united, and we need to be able to transform the information from big data systems into smaller amounts that can be handled by the conventional systems. So a very important area, and it is extremely useful for organizations to combine a big data insights with the knowledge that is in their conventional systems. As big data is a relatively new area, you will find that there are not enough people who are competent figuring out how to process this data. Not only processing, it is not only about analytics, but we also need to manage this data. We need to govern this data. Finally, we need to analyze the data in order to provide very useful output for the organization. And finally, politics, organizational silos. In many organizations, there is a fight who is going to deal with big data. There are parts of organizations that are afraid of change and they don't want to deal with big data. On the other hand, you may have the programmers who find the opportunity to do something useful with data, and the data organization may feel that the developers are stepping onto their toes. So organizational silos are one problem in introducing successful big data organization. We have seen a set of problems with relational databases and big data. Now we are going to outline the key approaches that help us deal with this problem. First, we have the new processing approaches. Among them, the most significant is the MapReduce algorithm, which is at the heart of the Hadoop approach. MapReduce algorithm is a relatively old algorithm that's covered in the 50s, and it is used in mathematics and later implemented in language Lisp. And somewhere around 2004, it got some attention as potentially very useful in big data problems. After that, we had a whole range of different algorithms that emerged. We have seen some algorithms that are newer, dealing with datasets primarily in memory, as we see in Apache Hadoop. There are some other approaches, for example, in Apache Flink. These are all descendants of Hadoop and MapReduce. And besides those, we also have some newer data technologies that span data storage and data processing. The most significant player here is Hadoop with its HDFS, Hadoop Distributed File System, which enables us to store very large amounts of files across many machines. And we can do that in a redundant way. And then we split the processing across these many machines. Not only Hadoop, we have a range of different data stores which use different techniques and different mechanisms. They typically don't deal with such huge volumes of data as Hadoop, but we are still in the area of big data. And we are going to see different flavors of NoSQL stores that we have. One of the more recent developments is the emergence of stream processing. With stream processing, we are handling data that is continuously coming into our system, and we are typically processing data within some window of time, and we are providing a real-time or near real-time results. As you can guess, there is not one silver bullet, and in many of our applications, we will be combining different solutions. We will combine Hadoop with some NoSQL stores and streaming, and this is how we will cover the needs of our applications. Let's see now what are some of the challenges with relational databases. We are going to use a simple diagram. On one axis, we are going to show the volume of data that we are trying to process. And on the other axis, cost of our database and the equipment. If we look at the cost of our equipment, the storage space and the processors, we see that we can achieve a fairly linear cost. If we need 2 times more space, we need to pay 2 times more. When it comes to CPUs and processing power, we don't get much faster CPUs than before, but we can get them in larger numbers. So multiprocessors and multi-core systems are becoming the norm. Now, if we put in this perspective the cost of our relational database systems, we will be surprised that the cost does not behave in such a linear fashion. So we see that when you start with relational database, your cost is low. You may start with some open source, small database. Later you graduate to some of the more commercial systems. Eventually you end up with fairly large systems, and then they are going to be very, very expensive. And there are two problems here. One problem is that the processing is relatively slow. The more data we have, the relational databases are going to become slower and slower. And then for large volumes of data, we are going to pay a really high price in order to be able to have relational databases that can handle those. Not only that, but when you're dealing with truly large volumes, you are going to have problems that relational databases cannot handle them. And that was actually one of the motivations that we have seen in the companies that started processing data on the web scale. Companies like Google and Yahoo, they have figured out that relational databases simply cannot store the data that they would like to deal with. What we would like to do is to find a solution, find a technology that would be able to take the cost of the relational database and flatten it, make it behave more like the cost of our storage and our processors. So we would like to avoid the exponential cost of such systems. We would like to have a linear dependency. And the other issue that we would like to address is that we would like to be able to handle data that cannot be handled with relational database systems. So there are two factors. One is improving the performance, reducing the cost. And the second issue we would like to address is to enable us to deal with data that the relational databases cannot handle. Now, this is where the categories of systems like big data systems, Hadoop, variety of NoSQL systems come into play. They are trying to address different aspects of these problems and enable us to have the processing of larger volumes of data much faster than we do that today with relational databases. You will see that there is no silver bullet. We are going to explore several different technologies. Each of these technologies is going to have its sweet spot. Some of the technologies, like Hadoop, is going to focus on handling this largest volume of data. Some of the technologies are going to focus on processing of data in real time, handling streams of data that are arriving into our systems. Some others are going to focus on representing data, which format may vary, and where you cannot find a schema that you can subscribe from the very beginning. Some other systems are going to focus on storing information as graphs with large number of nodes that are connected with each other. In the rest of the course, we are going to explore these approaches, and you will learn how to find the system that will be the best match for your application. In this section, we will introduce the foundations of Hadoop. Let's see how we would process large volumes of data with many machines. The first thing that we would need to do is to load a large set of records onto a set of machines. That would typically mean that we would need to split this data so every machine gets one subset of data. The next thing we would do is we would take the records that are on each machine and we would do something with these records. Sometimes that would mean extraction of some interesting piece of data. Sometimes we would transform the available data into something new. Now, each of these machines is going to process the subset of data that is residing on this machine. But you can imagine that if we need to arrange the data, we would need to move the data to go from one machine to the other. Usually, we would like to have that data with the same primary key would be all processed on one machine. So this is called shuffle. We are going to shuffle these intermediate results between the machines. The next step in our processing is going to be to aggregate these intermediate results. We will aggregate them and then eventually we will store the end result. Using this approach, we could deal with more data than it can fit on an individual machine. If you think about this algorithm, you would say that it is not very efficient, but if we have many machines, we could achieve a great deal of efficiency. There are a couple of things that we would like to do with this data set. First, we would like that each piece of data is described as a key and a value. What is key? It does not really matter. Let's say if we have a large text file, it can be just the number of line of text in this file. The value can be anything. It can be text, it can be a JSON, it can be some binary data. It doesn't matter what it is. In the technology of Hadoop, this first step in which we are extracting or transforming something of interest is called the map step. The shuffle in Hadoop will be supported by the framework, and we don't need to program it explicitly. And then when we are aggregating these intermediate results, this step is called reduce. So having the data with some keys and values, having the map function and reduce function that we execute on many machines, this idea represents the foundation of Hadoop. In this section, we will see how MapReduce algorithm works. So we are going to explain MapReduce on a little example. Imagine that we have a file, pets.txt, and imagine that is a very large file that contains various entries, dogs, cats, birds, and so on. What we would like to figure out is how many dogs, how many cats, and how many birds are in this file. So what are we going to do first is we will start from this pets.txt file, and then we are going to split it into lines. So we will have each line that will contain some of our pets. What we will do next is we are going to map these lines, and we will extract dog, cat, bird, and we are going to generate pairs, dog and number 1, cat number 1, and so on. And we are going to do that for every pet that we find in the file. As you can see, this is a very primitive function in which whenever we encounter a pet, we emit a pair with the pet kind and the number 1. This step in processing is called the map. So we take the output and we transform it, or we extract something interesting out of it. Then we are getting to the next stage in processing, which is called shuffle. In the shuffle, we are going to move all of these entries, so we have all dog entries in one place, or cat entries in one place, and then finally birds in one place. What we will do with this shuffle is that now we have all the dogs in one place, and then we can aggregate the values. And this is done in the next step, which is called the reduce step. And we find that we have 4 dogs, 3 cats, and 2 birds. When we get the results of this reduce step, we are going to put this all together into our result file with pet frequencies. Now, if you look at this algorithm, you're going to find that there are a couple of things of interest. First, there is a map and reduce function. This is something that we would have to program on our own. But if you look at the shuffle, you can see that shuffle can be done quite mechanically. We are going to take the kind of pet, we can use it as the primary key, and we are going to put all the values that have the same primary key in one place. Now imagine when we apply this algorithm to big data processing, we can have that all dogs are going to be processed on one computer. And then in the reduce step, we are going to collect these results and eventually store it in some files. So as you can see, MapReduce algorithm would profit a lot from brute force approach. If we have many machines on which to execute map and reduce, we can really improve the speed of processing, and we can distribute our effort across many machines. Now, looking into the MapReduce processing model, let's summarize a couple of interesting points. First, our input is going to be split into pieces. Different machines are going to process individual pieces. And these machines, we often call them worker nodes, will process these pieces in parallel. So we could gain a lot of efficiency by having many machines. Now, if you think how is this going to run on actual machines, you can imagine that the results can be stored in local files, and then the reducers, which are also going to run on these machines, would be able to access these files and process them. So in the reduce step, we typically perform some aggregation. We are reducing the values that we have obtained from the map steps. And as we have done with the map step, we have a number of machines that are engaged in this processing. Looking into programming this type of systems, you can see that here we can talk about separation of work. We have programmers who would need to provide map and reduce functions. We will see various ways how this can be done. One can use a language API, for example, in Java, a bit tedious, but it gives us full control over the process. Or one can use some of the higher level languages or libraries that improve programmers' productivity. But the beauty of Hadoop and MapReduce algorithm is that the programmers can focus really on map and reduce functionality. There is a whole set of areas that are dealt with the Hadoop framework. One of the most important things when we are dealing with larger clusters is dealing with fault tolerance. The machines are going to die, and we still need to provide a reliable processing. Programming a fault tolerance in systems is a very difficult task, and very few programmers are having sufficient experience and knowledge to do it. The other interesting thing is that if you think about a solution in which we have lots of data stored on these different machines, we will have the assignment of worker machines to map and reduce tasks. This can also be done by the framework. Now, one of the very interesting things with big data framework like Hadoop is that we will actually move processing to where the data resides, because we have a very large volumes of data, and it would be very inefficient to move this data through the network to the processing. And this is something what we do with conventional database systems. We remove relatively small volumes of data. The other thing that the framework can do is this shuffling. So moving of data from map processing to the reduce processing is something that can be done by the framework without need to program that. And finally, one of the interesting areas is dealing with errors. Our programs may experience various errors, and we need to provide solution to handle those errors. Now, these are all the benefits that a framework for applying MapReduce can give to us, and so dramatically improve our productivity, so we can focus on providing this map and reduce steps. Before we go into the programming of Hadoop, we will need to understand a little bit better how Hadoop works, and that will be the goal of our next sections. In the previous section, we have seen MapReduce as the foundation of our approach. Now we are going to look into Hadoop as a software system. Hadoop, by its definition, is a framework for processing large amounts of data that is spread across multiple machines. It is an open source framework, and it is designed from the very beginning to work on clusters of machines, where these machines are not necessarily some high-end, expensive, extremely reliable computers, but cheap and unreliable machines that can fail anytime. That is why fault tolerance is such an important place in this framework. The ideas of MapReduce have been implemented at Google, and Google was using these to process the web pages that the company was using to build index for their search engine. Google has its own proprietary implementation, and Hadoop is the realization of MapReduce and associated techniques in Java and made open source. The foundation of Hadoop, or the key idea, is that the whole system is designed to scale. So if you need to add more processing power, it should be relatively easy to add more machines to your cluster, and that is how you achieve efficiency in processing. Naturally, Hadoop was very popular in companies that are processing large volumes of data, particularly web data, but we have seen that more and more enterprises are embracing Hadoop, and it is now one of the cornerstones for processing large volumes of data. Now, when we talk about these large volumes of data, we are not necessarily talking about petabytes of data. One of the very informal definitions of big data is that more data than you are used to handle. And in such settings, Hadoop can have a potential to be a very cost-effective solution, even though that you can be using some of the relational technologies of the past. Normally, what you will see is that Hadoop is going to be combined with existing systems and some other NoSQL stores, which is going to be the topic of our next sections. Hadoop has two essential parts. The first part is the MapReduce framework. We have seen the MapReduce algorithm, and one of the key things in Hadoop is using the MapReduce framework for processing, and there are also some maintenance tasks that needs to be done. For example, the work needs to be assigned to different machines that are part of the cluster. Dealing with fault tolerance is the other thing. And this is where we have Hadoop Distributed File System, or HDFS. In HDFS, we have a mechanism for storing data over multiple machines in a redundant form. So HDFS acts as a file system that would span the nodes in the Hadoop cluster. And the idea is that the data will be stored in a redundant fashion, so that even if some nodes fail, we can still have the data that can be used for processing. One of the interesting things is that these systems can be made self-healing, and that is when you bring in another node that is replacing the dead one, you can reconstruct your data on this node as well. One of the very interesting features for us with HDFS is that in many ways for the user, HDFS behaves like an ordinary file system that is approached through a slightly different interface. And we have an illusion that we are dealing with an ordinary file system. In this section, we will explore the Hadoop distributed file system and the ways of interacting with it. Now, if you are thinking about how would you store data that is used for MapReduce, the first requirement that we have is that the data needs to reside on multiple machines. The second requirement is that we should be able to store any type of data. So the data does not need to neatly fit into tables like in relational databases, but it can be unformatted data, it can be text, it can be images. So we don't have any particular requirement on the type of data that we are storing. And here we have one problem. The first problem is that as we are running on a cluster with many machines, there is quite a bit of likelihood that at some point one of these machines is going to die. And if a machine dies, we don't want to lose the data. So one of the critical parts of Hadoop solution is how do we store the data on multiple machines without encountering loss of data if something dies. The idea that we have is to create a distributed, reliable storage. The question is, how would we do that? The solution for that is the Hadoop distributed file system, and we will see now how it works. The first thing that we do is we are going to take a large file and we are going to break it into blocks. These blocks will be stored on multiple machines. We call them nodes. So each of these machines is going to get a subset of data. And you can see here, node 1 is going to have some fragments of this data, node 2 is going to have something else, and so on. Here on the left, you see the master node. A master node has a special purpose in the Hadoop cluster, and it contains the part which is called the name node. A name node has one important piece of information, and that is it knows on which machines are which blocks residing. So it is almost like a table of contents. The next thing that we have with our Hadoop distributed file system is the replication. In order to achieve a fault-tolerant solution, a piece of data would need to be stored on multiple machines. And here we have in this illustration our fragment of data number 1 is stored 3 times. And in fact, this is the default replication of data in Hadoop cluster. So every piece of data is stored 3 times on different machines. One of the things that you need to think about is that we are actually using more space than it's really necessary for every individual piece of data. But we don't worry about that. The disk is cheap, and what is important is that we have the fault-tolerant solution that can survive a death of a machine. Now, if you think about some other solutions that we have in this space, for example, RAID drives will also store data in redundant fashion. When we are storing data on the Hadoop cluster, typically we store the data on plain ordinary drives, so without using any RAID mechanism. Looking into the HDFS, we can say that the data is first split into blocks, and then the data is distributed across the machines in the cluster. And by default, each of these blocks is replicated 3 times. One of the interesting things that we have is that the machines that we have for our clusters are fairly cheap machines, and they tend to be relatively unreliable. They are not using the most expensive and the most sophisticated hardware. So we expect that these machines are going to die. Our HDFS provides us with a reliable solution where we don't lose the data. HDFS, in its realization, resides on top of native file systems. And normally, these machines are running Linux, so HDFS resides on top of that. We have seen in previous illustrations that we have some blocks, and that these blocks are typically going to be relatively large, 64 to 128 megabytes. And all of these ideas that we have in HDFS are following the ideas that were originally created for the Google file system, which remains as a proprietary implementation. So now when we are thinking about how should we apply HDFS, should we better work with many small files, or should we better work with fewer files that are rather large? The sweet spot for Hadoop is to use a smaller number of large files. And the typical size of these files is going to be over 100 megabytes. Now, when we are thinking about our processing, and you may remember when we explored MapReduce algorithm, we were reading the data from beginning to the end. And this is something that would be important for HDFS. you don't have the random access to piece of data in HDFS. So you normally read your data from the beginning to the end. And why is that good? This is good because it minimizes the cost of seek. And we don't do updates on such files. If we need to write something new, we would put that typically in a new file. So you need to remember, when you are dealing with Hadoop and HDFS, there is no random access. We will see later some solutions that reside on top of HDFS that will allow us to do some changes. And that would be the HBase, which is the database that runs on top of Hadoop. We said that we have fault tolerance, and for that we have a replication. The default factor is 3, but you could also go higher in some situations. Let's see how are we going to interact with HDFS. The most common way of working with HDFS is through the HDFS shell. You will be working in a terminal, and you will have various commands that all follow the form. So first there is Hadoop, then you may have some options for configurations, then there is the command, and then you can pass either generic or command options. We are going to see a couple of examples of these commands. Now, you also have an alternative, which is a web user interface. Today, every Hadoop distribution is going to have some very convenient user interface, typically through a browser, that will enable us to work interactively with files, like in a file browser such as Finder or Windows Explorer. Now, there are some open source solutions, but many vendors are providing the added value. They are always trying to provide something extra, and proprietary solutions differ in their usability. For tool builders, there is also Java API. We are not going to talk about this API. And also there is the REST, so you can interact with HDFS using web services. When you're working with HDFS, you are interested in doing two primary things. One thing is to get the files from your machine into HDFS. And the second thing is to get the data from HDFS back onto your local machines. One thing that you need to remember is when you process your data with Hadoop, the files, the results, they stay in HDFS. You need to move them to your local machine on your own. The first command we are going to see is the get command. Get command is going to copy the files to the local file system. So you have some file in your Hadoop cluster, you want to move it back to your machine. And the command is going to look like this. There is Hadoop, then fs, we are dealing with file system, and then there is a -get. After that, we have the file in HDFS, and the second parameter is the name of the file in your local file system. Put command is doing the opposite thing. It is going to copy file from one machine into the HDFS, and you can see here the example of how that looks like. Now, there are two related commands, copy from local and copy to local. They are simplified versions, and they are restricted to local file references only. Besides that, you will see that HDFS resembles an ordinary file system, and you are going to find all of the commands that you would expect to find in a file system, like in a Linux. For example, you will have cat, copy, ls to list the files, make directory, move files, and so on. So all the usual suspects are there. We are going to explore the key elements of the Hadoop infrastructure. First, we have name node. The primary purpose of the name node is to manage the metadata for the HDFS. Now, considering that no processing on a Hadoop cluster will happen without HDFS working properly, one of the key tasks for the name node is to remain accessible. And that would naturally lead us to install it on a machine that should be more reliable than the nodes on which we are doing the processing. The metadata, which is the information about our files, is held in RAM. And this is why the machines that are running the name node, they should have a lot of RAM. Another term that occasionally shows up in discussions of Hadoop is the secondary name node. And many people believe by mistake that this is the backup for the name node for high availability. And that is not correct. Secondary name node is not a backup, and its purpose is to offload some of the housekeeping tasks to another machine. The second part of our hardware infrastructure consists of data nodes. Data nodes are going to do the processing, and they also store the data in normal files. We have seen that HDFS is built on top of the ordinary Linux file system. Now, the name node is going to access the data in the HDFS cluster, and the name node needs to know what are all the different blocks that are needed to assemble a file and treat it as one unit. So the programs will read the data from data node directly, having direct access to the data. And we already mentioned that a typical organization is that the large files are split into blocks, usually 64 or 128 megabytes of blocks. And having larger blocks makes for easier management. Our processing consists of map and reduce tasks, and these tasks are running on our data nodes. One of the interesting things here, which makes Hadoop different from traditional processing of data with databases, is that we are not going to send the data to the program. Instead, we are going to send the programs, in our case, our map and reduce jobs, to the data nodes, and the processing will happen there using the data which is stored on the local disks. If you think about how this map and reduce tasks run on nodes, we can examine a cluster. In this cluster, we have a set of nodes, here represented in blue. These nodes contain data, and these are our data nodes. On the left, you see the master node, which also has the name node. When you write MapReduce program, the first thing that you will do is you will copy this MapReduce programs to each of the nodes that contain data. So this copying is the first part of our processing. And the map and reduce jobs will process the data that resides on the disks of these machines. Naturally, you need somebody to coordinate and keep track of the execution, and that is the purpose of the job tracker, which executes on the master node. Now, when you have this Hadoop infrastructure, you need to manage it in some way. You need to deal with standard tasks like starting and stopping the servers, adding and removing the servers in our cluster, and also you may want to view what is happening on a particular server. You may want to examine the log files. In the beginning, the Hadoop management tools were rather sparse, but as Hadoop was getting more and more mature, we have seen that there is a larger number of tools. Some of them are open source tools, but particularly vendors who are providing some additional value on top of the open source are coming with very appealing user interfaces that allow us to very effectively control our Hadoop clusters. Yarn is the software part of a modern Hadoop infrastructure. Yarn stands for Yet Another Resource Negotiator. Its origins are from trying to figure out how to solve the problems that we had with the early version of Hadoop. First of all, we had problems with multi-tenancy. Dealing with multiple tasks and nodes was quite a challenging problem, and what we would like to do is to manage multiple jobs on a cluster. The other problem was related to scale. There are some large users who wanted to scale Hadoop jobs beyond 4,000 nodes and deal with the problems that we experience in such large deployments. So Yarn is an internal reorganization of Hadoop. The good thing for us is that the API is compatible with the original version of Hadoop, so not much changes from the end user's point of view. Yarn provides a whole set of benefits for us. Yarn is a layer on top of HDFS, and it provides the common platform on which we have various systems and tools. For example, we have Pig and Hive, which are the languages for programming MapReduce tasks. There is HBase, which is the real-time database on top of Hadoop. There is Storm, which is a system for processing streams of data. Solar, the search system. Spark, a system that allows us to process big data, which is focusing on keeping as many data as possible in memory, achieving speed. We have Cascading and Scalding, which are the libraries for very productive programming of Hadoop jobs. And we have a variety of newcomers to the Hadoop system. So Hadoop system is expanding, and having a common platform for resource management is one of the foundational elements of the Hadoop. So we say that the Yarn is a common resource management layer for applications that provides us with scalability. It gives us better cluster utilization, and it can also handle workloads that are different from conventional MapReduce. For users, Yarn is a welcome addition because it gives us more flexibility in the way how we use Hadoop, but Yarn is typically hidden from end users, and we just enjoy a variety of tools and systems that run on top of it. Let's see now what are our options when it comes to programming Hadoop. The most important thing to think about when you are programming Hadoop that you cannot do any updates in place. So you can process your files, but the results are going to be stored in a new file. So Hadoop does not provide you an option where you can access a very large file and then do some update in the middle of that file. The second thing that you need to consider is which approach are you going to use when it comes to programming. We will see several choices, and they will differ in their complexity, they will differ in their ability to control the Hadoop, and also the productivity. And finally, you should consider the developer background. Some of the approaches are better suitable for programmers, while some of the approaches are going to be more approachable to data professionals. Our first option is going to be Java. Java provides us with the fairly low-level API, but it also gives us a full control of all aspects of MapReduce because Hadoop itself is written in Java. For writing daily Hadoop tasks, you will find that Java API is a bit cumbersome, and you typically need to write quite a bit of lines of code in order to achieve even a simpler task. But again, you have a great control. If you still want to stay with Java, but you would like greater productivity, you should look into Cascading. Cascading is an open source Java library, and you program by assembling data flows, and these data flows get translated to MapReduce jobs. So Cascading is a very good option that combines the full power of a programming language and also gives you a higher productivity. Easier than the native Java APIs, we have Hadoop streaming. Typically, they will be used by languages like Python and Ruby. The model is simpler than using Java APIs, but it is also less efficient. The way how you would work with Hadoop streaming is that you would write map and reduce functions. The input will go as the standard input stream into map function. The results of that will be written as standard output, and that would feed in the input of the reduce function. And finally, the output creates the resulting file. So the model is fairly simple. The code tends to be much shorter than the Java code. Our next choice is Hive. Hive is a SQL-like language, so it is a great starting point for data professionals. You will find that Hive is significantly more productive than Java, but the SQL that is used by Hive is not as rich and powerful as the SQL dialects found in modern database systems. Still, we can extend Hive by writing various user-defined functions. Hive is a great starting point for experienced data professionals. One of the possible drawbacks of Hive is that as you are writing SQL, you may have to write a complex SQL statement at once, so it may be difficult to write Hive programs little by little. Pig is addressing this issue. Pig is a data flow language, and its advantage is that we can build our programs out of small steps. So you can write a line, try it out, write the next line, see how will that work, and so you have a fairly iterative and incremental way of building your Hadoop programs. Productivity is similar to Hive, so much more productive than using Java APIs. But Pig itself is designed to handle relatively simple flows, so there are no control structures or iterations, and we can extend it using user-defined functions. Our next choice is Scalding. Scalding is a library that is built on top of Scala. Scala is a modern programming language. It is a descendant of Java. It runs on JVM. It's compatible with Java programs, and you can mix and match Java and Scala parts of the program. Scalding has a very elegant model. The programs will look like we are manipulating in-memory data structures that are coming from standard Scala libraries, things like collections, lists, and so on. And these programs will then get translated into MapReduce. The programs tend to require very few lines of code, which are also very easy to read and understand. And one of the things that we like about Scalding is that it is built on Scala, it is a library, so we get to enjoy the full development ecosystem, which consists of modern IDEs. We also have the tools for continuous integration testing. We will explore different options for programming Hadoop in more detail in the following sections. In this section, we will explore Hive. Hive is a data warehousing infrastructure based on Hadoop. Its key characteristics are a massive scale out and fault tolerance. When we say scale out, that means that we are achieving greater performance not by running the system on bigger machines, but that we are spreading the processing across a number of machines. Hive originated at Facebook in 2007, and now it is a part of Hadoop project, and it is part of Apache. The way how we work with Hive is by using HiveQL, which is a query language based on SQL. The way how we work with Hive is by first defining tables. And the way how we do that is by defining a mapping on top of HDFS files. So the interesting thing is that we will not be creating real tables. We will be establishing the mapping between the files in HDFS and the tables that are logically used by the HiveQL. When we run our queries, these queries are going to be transformed into MapReduce tasks. And one query can be reduced into several MapReduce tasks that are chained together. Now, when would you consider using Hive? Well, Hive would be a good candidate when you have people who are experienced with relational databases and they need to make a transition to Hadoop. HiveQL is going to feel very familiar. You have the language that is very similar to SQL. You have the notion of a table, which is not exactly as what we have in a relational database, but is fairly close. What are the typical applications that we program with Hive? The processing model is that we store data that might be coming in various formats. That can be text, that can be some comma-separated values, that can be even images or some non-structured data. And then we will apply SQL-like tools and processes to create useful information out of them. The typical applications are processing of logs, processing of text, indexing, ETL, business analytics. So many of the conventional applications can be programmed using Hive. Now, the interesting thing is that it is all files. The tables that we define in Hive are actually just the mapping over the existing data that exists in the files. And the Hive will operate directly over the HDFS files. So when we create a table, there will be no separate storage that will be allocated. One of the nice features of Hive is that we can partition the tables. And we can do that by the region or by the date. So we can reduce the processing of files to only those that are of particular interest for our queries. In working with Hive, we typically follow a workflow in which we first collect our data and we dump this data into HDFS. We are going to create the mapping between the Hive table definitions and these files. We will run the queries, and then the result of these queries is stored again in HDFS. And then if we need these results for our conventional data processing, we can move this data into our regular file systems. Now, when we are running our queries, Hive creates the needed MapReduce jobs. And as we mentioned, you can have a number of MapReduce jobs that are being executed in a chained fashion. Now, the nice thing about this workflow is that for the users, we have the impression that they are working with some variant of SQL. So let's see our first piece of Hive. We are going to do a table mapping. So we will be creating a mapping for dealing with logs from Apache Web Server. So we begin our code by saying that we are creating a table, Apache log. Then we will be defining various fields like host, identity, and so on. We are going to have a number of those. And then we will say, what is the row format? There is this word SERDI, which means serialization, deserialization. And what follows is the name of the Java class that is providing this service for us. So this is some library that we are getting from the Hive part of the Hadoop. And then we define various serialization, deserialization properties. The one that we see now is the input regular expression. And this is the regular expression that describes the Apache logs. That is not something that you would invent at this point, but you will look it up and see that it is a good match for what you want to do. And then we also define the output format that will match our needs. And then at the end, we say that this is stored as a text file. So to summarize, the interesting parts and parts that are specific to Hadoop is the area where we define the serialization and deserialization properties, and then we have the description of this raw format as a regular expression. As a reminder, this is just establishing the mapping. No separate space is created for the table. Running the queries is going to look very familiar. So here is a query where we are selecting entries where host matches particular IP address. And as you can see, this really looks like a plain SQL. So the query language is a subset of SQL. The compiler is going to convert it into a set of MapReduce statements. So if you think about it, this is going to be a great advantage for Hive. The API is very productive. It's more productive than Java. And one thing that you might be surprised by when you run your Hive queries for the first time is that you will be facing a batch execution. So when you run such a Hadoop job, it is going to take some time to execute it, 20 seconds or even longer depending on your system. In this section, we will explore the Hive architecture. Hive architecture consists of several pieces. First, we have the Hive itself that consists of a couple of areas. It has the command line interpreter, it has the web interface, and then the most important part is the driver. The driver includes the compiler, the optimizer, and the executor. One thing that Hive is using is the metastore. Metastore contains information about tables, privileges, and so on. And when the compiler creates the MapReduce jobs, they will be executed on the Hadoop cluster. So the result of the compiler's work is the program that will be running on multiple nodes. If you look into Hive and compare it with relational databases, we will conclude the following. First, both Hive and relational database use SQL. Hive is suitable for analytics jobs, while the relational databases can be used both for online transaction processing or analytics. Hive is going to serve only batch workloads, while the relational databases can be used both for real-time or batch. For a conventional database practitioner, probably one of the big surprises is that there are no transactions. And this is actually quite common in many distributed systems. So various NoSQL and big data systems that operate over a larger number of machines simply avoid dealing with transactions because they are very expensive to perform in such a distributed setting. Considering the way HDFS works, Hive does not have insert or update, but the results of our work can be added as new files. And here is the area where Hive is going to shine. This is the distributed processing. Hive can be run on hundreds or thousands of nodes, while the relational databases have much more modest limits when it comes to distribution. And the great thing about Hive is that we will achieve a really high performance on commodity hardware. Usually the way how we run Hadoop and Hive is on a larger number of relatively modest machines. And here we have one additional advantage of Hive. We can store very large amounts of data very cheaply. So if you compare the price with relational database and the Hive, Hive is going to be superior. And this is why many people in industry are considering Hive to be the next generation enterprise data warehouse. It will not be a full replacement for a relational database, but there are certain areas where it has significant advantages. Hive and MapReduce are tightly related to each other. The Hive query will get translated into one or more MapReduce jobs, and they will be chained together, and these jobs will be executing on the Hadoop cluster. Thinking about programming for Hadoop, in the previous section we have seen a brief overview of different approaches, and we have stressed that Hive is much more productive than Java. For everyday works, it is much easier to write HiveQL. You will also have to write much fewer lines of code in comparison with Java. So we have a significantly increased productivity. One piece of Hive that is interesting is the metastore. Metastore is actually contained in a relational database. And this database is internally implemented with an object relational mapping system from Data Nucleus, which is a very popular and portable system. So it is very easy to migrate Hive metastore to different relational databases. What about the size? Well, it is only metadata, so the store is not large and you can use a variety of database systems for it. The default implementation is done with Apache Derby, It's a pure Java, lightweight relational database system. It is good for development, and in production, we are typically going to replace it with MySQL. How do we interact with Hive? There is the command line interface. There is also web interface. Usually, commercial distributions of Hive are coming with a nice web interface, but there are also language clients, so we can include Hive in our programs. What is interesting is that in Java world, you can just use JDBC, and your URI is going to look like this, JDBC with the Hive as protocol, and the rest is the same as with normal databases. There are various bindings for Python. There is also binding for ODBC, and so on. The number of clients is growing. Let's see the Hive data model. When we talk about Hive data model, the first thing that we will experience is that data model looks very familiar to traditional relational database layout. In fact, one interesting thing is that there is no such thing as the actual Hive format. The Hive data model is actually just a mapping to files that reside in HDFS. So, in Hive, database is just a namespace for separation of tables. And the table is some unit of data with the same schema, and that follows the familiar format, where the tables have columns, and the columns are mapped to the different parts of files in HDFS. A very powerful and convenient thing in Hive data model is the presence of partitions. Partitions are optional, but very useful for structuring larger datasets. A table can have one or more partition keys. Very common ones are date and the country. And what is interesting is that each value of a partition key defines a partition of the table. So, for example, you can limit your queries on files that are defined for the country US. You can limit your files for the particular date, and you can have a combination of different partitions. The interesting thing here is that these partitions are actually virtual. They don't really exist as columns in our dataset, but they are actually derived on load. Another convenient feature is the presence of buckets or clustering. And the data in a partition can be bucketed based on some hash function that is taking input from a column in a table. For example, we can do the bucketing based on some user ID. Why would we do that? Well, both partitioning and buckets are a very convenient way to speed up the execution of our queries by pruning the data that we have no interest in. Let's see now the Hive types. First, we have primitive types. They are similar to SQL. We have strings, integers, booleans, timestamps, and so on. In addition to those, we have some complex types. And these are the types that you will not find in the relational database. We have arrays. For example, we have arrays of integers or strings, and we can use the brackets for indexing. We have maps. Maps will act as hash tables, and we have, again, the way of accessing those through brackets. We also have structures. They are represented as arrays, and they can be columns of some more complex types. And we will be accessing them by using a dot as the separator. And finally, there is a union. A union first has the tag that describes what is the kind of value, and then we have the value itself. Now, let's see something practical. How would we create a table in Hive? So we are going to create a table that can be used by an e-commerce system, and this keeps track of product views. So we have some product ID, we have the user ID, time of the visit, and we have the IP address. We will show here how do we do partitioning. So we are doing partitioning by the date and by the country. And this table is going to be stored as the text file. In Hive tables, we use the ASCII character 001, which is Control A for delimiting data, and new line is the row delimiter. You can also configure your data delimiter. Now let's see how would we load some data. One of the very common scenarios is to create a table at the location where we already have some content, where we already have some file in HDFS. In order to do that, we are going to say that we create an external table, for example, product view row, and then we have certain columns, product ID, user ID, visit time, IP address, and country, stored as text file, and now the critical part, location, and where is the location of this file. So what would we do with such table? One of the common things would be for a user to copy a file at this HDFS location. For example, here we are saying Hadoop DFS put, and then what is our file here in our temporary directory, and we put it in the location of the table. And then the user can transform the data, can refine it, can extract something interesting, and in our case, we are going to access this raw data and then insert override table. This is how we get results of our queries in new files. We can indicate what is the partition that we are creating, and then there is the query with select and the where clauses. One of the things that we can also do is we can load the file into Hive table when the data format is the same. For that, we can use the load data local. In pass, we provide the location, and then we are saying into which table are we loading this data. And then we can also indicate what is the partition. Hive queries are quite similar to queries in relational databases. One of the important things to remember is that if we want to save the results of our queries, we always have to store them into a file. This is why you will see when we run the queries a statement insert override table, and then it is followed by the table, or we can write the files into a directory. When we are running Hive queries, we can run these queries from our programs, but we can also run them from the user interface or the command line. But one thing to remember, when you start experimenting with it the first time, Hive is a batch, so it may take a while to see the results. When we are running Hive from the command line interface, the results of the queries are first stored into a temporary file, and then they are presented for us. Let's see some queries, and in our example, we will see a query that is also using partitions. For our e-commerce application, let's create a query in which we are going to select certain products. So we will start by saying insert override table, Gizmo product view, select product view. We are getting all fields from this table. And then we will say we are doing from product view with a condition. Product view date is after 1st of January and before the end of January. And the product ID is Gizmo001. So this query is interesting because it is also using a partition, which we have defined as a partition by date, time, and country. We can also do joins. Joins will follow the similar form as in relational databases, where we are going to say, for example, from customer C, join product view PV on particular condition that the customer ID is the user ID of the product viewer. For the join control, we have our usual suspects, left outer, right outer, and full outer. And for best performance, it is best to put the largest table to the rightmost position of the join. And as a reminder, when we execute our queries, we want to store our results. And this is why we are always using insert override table before our select statements. The result is stored in HDFS, and we can keep it there. And we can use these results for the next queries, or we can export it back into our local file system. When you work with Hive, you will notice that the number of functions that are defined are somewhat lacking in comparison with modern database systems. This is why we have possibility to define user-defined functions, and we have three kinds of those. We have first, simple user-defined function that is going to do one-to-one row mapping. An example is a concatenation function that can combine first and last name. Second, we have user-defined aggregate functions that can do many-to-one row mapping, for example, doing a sum of sales. And then finally, we have user-defined table function, which is going to do one-to-many row mapping. An example is explode, that will take an array and it will create 3 rows. Now, let's see when would we use Hive. The first thing that comes to our mind is to use Hive when we have very large amounts of data. So massive data, dealing with SQL is a big advantage, particularly for people who already have a relational background. But there are a couple of things that you need to keep in mind. And that is, you need to watch out for limitations. First of all, there is no update. There is no single row insert. And you will typically find that you will be lacking some of the functions that you are used to seeing in a SQL of modern databases. But fortunately, you can write your own extensions using the user-defined functions. Another thing to remember is that Hive is running on Hadoop, and that this is a system for batch processing. So real-time response is not going to be a good match for your Hive queries. Dealing with batch processing is fine. Now, when you are thinking about Hive, if you are not really tied to using SQL, you should consider some of the alternatives. For example, Pig can be a very good replacement for Hive, and we have seen in some organizations they may start with Hive because of the similarity with relational model, but then writing a longer Hive queries becomes increasingly difficult, and some teams figure out that it is easier to use Pig, as they can write their programs line by line, try it out in small increments, so they can grow program to the full functionality. Another alternative is Scalding. We said that Scalding is a domain-specific language or a library that is running in Scala, and that will give the advantage of a full programming language. You will be able to do iterations, which are very important if you're writing something that involves machine learning. And Scalding can also fit in the full development cycle because you have the continuous integration, you can use test-driven development and similar. Let's see now when to use Hive. Hive is not necessarily the best choice if you don't have that much data. Perhaps an ordinary relational database could serve you better in that case, and you will be able to get faster responses. Alternatively, you may consider some of the other non-relational NoSQL stores. One situation where you don't need to have that much data and Hive can still be a good choice is if you are, for example, offloading processing from an existing relational database, but you may have a solution that is simply costing you too much money. Offloading processing to Hive can be a really good alternative. And we have seen that in many cases with the ETL processing, which is a very easy and often the natural first step in adopting big data. The second situation when Hive is not necessarily the best choice is if you are dealing with data that has no clear structure or schema. Perhaps you are dealing with images or video or something like that. And then finally, Hive is running as a batch process. So if you need a real-time response, you should look into some other solutions. In this section, we will explore Pig. Pig is a system and a language for processing of semi-structured data. The language was created at Yahoo around 2006 after developers have been tired of using the rather cumbersome Java API, which was providing great control, but it required quite a bit of lines of code even for relatively simple tasks. Pig Latin, the language, was created so that it is a procedural language. You will be writing execution paths, and that will remind you to writing ETL scripts. So we have a variety of functions for filtering, for joining, and processing our data. Pig Latin is a scripting language, so it is not going to be compiled, and it is a fairly high-level language in a sense that we are going to create our Pig Latin script, and this script will be converted into MapReduce jobs. The conversion will result in sometimes one, sometimes you will have several MapReduce jobs that are chained with each other. You will see that when you start working with Pig, there will be a set of functions that are already provided, but you will often need to create some additional functions, and you can do that. You can write your user-defined functions using either Java or Python. The bottom line is that when you're programming in Pig, you are significantly more productive than if you are using plain Java. When it comes to productivity, Pig and Hive are quite comparable with each other. How do we run Pig? We have several options. One option for execution is the local mode. This mode is going to be used when you are developing Pig programs on your machine, and it is using local file system. So in that mode, Hadoop is not involved at all. And this is actually very good. It will give us really good return time for our programs. It is very convenient for prototyping. And one of the additional steps that you will appreciate is that when you're writing your Pig programs, you can write them line by line. So you write a line, you execute it, you examine if you are happy with the output, write another line, you can rerun it. And that is very convenient to do in this local mode. So you have a turnaround that is just in a range of seconds. When you have tested your program and when you are quite confident that everything works well, you can switch to the Hadoop mode. And there the programs will be compiled into MapReduce jobs. They will be executing on the real Hadoop cluster, and this mode will naturally be used for batch execution. So the execution time of Pig is very similar to Hive. They are both going to run as batch processes. So lazy execution is one of the hallmarks. The language will be interpreted when needed, and the programs will not be compiled ahead of time. When you are working with Pig in your environment, you will be using Grunt. Grunt is a Pig interactive shell in which you can explore various commands. In the next section, we will see Pig's data model. In this section, we will introduce Pig data model. Pig types come in two forms. We have primitive types and complex types. One of the differences in comparison with relational model is that the model is nested, and that means that a complex object can contain other objects. The simple data types are all what you would expect in such a language. Integers, longs, floats, doubles. Character arrays are UTF-8 strings, and byte arrays are just blobs of data. Complex data can be organized as fields, which are just pieces of data, and then we have tuples. Tuples will be used quite a lot. Every row of data that we are processing is treated as a tuple, and the schema is optional. One important limitation of tuples is that they must fit into memory, and they consist of ordered set of fields that are denoted by parentheses. So for example, here is one tuple with 1001 Joe Smith and some value, something that we could use for sales. Other types that we have come in form of bags. Bags are collections of tuples, and they can contain duplicates. One really interesting property is that they do not have to fit in memory, and we call such types spillable, so they can extend onto disk. Bags are accessed in a sequential way, and for their elements there is no guarantee for order. Regarding the notation, bags are denoted by curly brackets, and here we have one bag in which we have two tuples. Maps are sets of key and value pairs. They are equivalent of hash tables, and internally they are really implemented with Java data structure hash map, where the string is the key and object is the value. Let's see now how are we going to load the data in our Pig programs. First, we have the load statement. With load statement, we will read the data from the file system, and we have several options. We have the load function, and the default function that we use is the Pig storage. The limiter is tab, and you can customize that. One of the alternative storage is JSON storage, JavaScript object notation, very popular in modern systems. And when it comes to schema, we assign a schema to the data, and we are saying that such schema is assigned on the fly, or we also say the schema is assigned on the read. So let's see a little example. So we are going to load sales data from a particular file. We are using Pig storage, where tab is the separator. This is optional because we are using just the default values. And then we can define what is the schema. So we have the user ID, which is character array, name character array, and sales amount is float. Storing data is achieved by using the store. So we will say store, for example, sales data into, and then we give the file. We have a couple of store functions. The common one is the Pig storage. There is also bin storage, which can deal with data that is split into multiple files. When you're working with bin storage, the thing to remember is that data lineage is not tracked. If you want to implement data lineage, you need to do that on your own. And then, of course, there is the JSON storage. In our next section, we will see how do we write programs with Pig Latin. In this section, we will examine the key elements of Pig Latin. We have a number of operations that work with data. We have operations that are filtering data, going through the elements of relations, joining multiple relations, grouping, and so on. When we run our programs, the data operations are converted into MapReduce flows. Let's see some of the key operations. First, there is the elementary operation for filtering. We can select tuples based on some condition. For example, imagine that we load some customers, and we provide a schema for these customers where we have the ID, which is a character array or string. We have a name for the customer and age. Let's say we would like to work only with those customers where age is over 30. We will write our filter statement and provide the condition. For each generate is the next operation. What it will do, it will generate some data transformations based on columns of data. So basically what we do with it is we perform some operation on every row. And here is an example. We will be going through the customers and we will be creating a new relation that consists only of the name and the age of the customer. Everything else is going to be ignored. So this is a very convenient operation because we can reduce the elements that are not needed. And this is actually one of the best practices of using Pig. This type of operation is called its projection. And it is very useful because it is reducing the amount of data that we need to work with, and that improves the performance. Group. Group is going to collect records with the same key into a bag. And as you can imagine, this operation is different from grouping in SQL. In SQL, grouping is going to feed into an aggregate function, while in Pig, the grouping is just that. So there is no necessary connection between the group and aggregate function, even though that we could do that. And as an example, we could group sales by user ID. And the result of that is going to be a tuple that will have the user ID. And after that, there will be all the sales with that user ID. Order by is going to sort the data. You can sort by using multiple keys. Syntax is quite similar to group. And in this example, we will take our sales data and we are going to order them by sale amount in descending order. When we are executing order by, this will always cause data to go through reducers. And one of the interesting things that can happen in real applications is that our values are often skewed, and the order by can actually do balancing across multiple reducers. So we can get a little bit of optimization there. Joins are combining tuples from bags, and we are going to join them using the specified join key. The default join is inner join, and here is an example. In this example, we are going to load some sales, providing the schema with the user ID, name, and sale amount. Then we are going to load some customers where we have the ID, name is character array, and age is integer. And you can imagine how are we going to do the join. We will say join customers by ID and sales by user ID. Result is the joined relationship. With Pig, you will not find all the functions that you can imagine, but that is not a big problem because we can write our own functions using either Java or Python. And that is the way to add some more complex processing into Pig. One thing that you will need to do is to register the jar file that contains the compiled Java program, and we will have to tell Pig where is this file, so it can load the user-defined functions. UDFs are commonly used with for each generate statements. In this example, we will go through customers, and we will be applying our own UDF function, myCustomerInfoUDF, that will take the ID of a customer and produce some more detailed information. And we are going to store it as the customer info. One of the things that is great about Pig is that we have a great support for debugging and diagnostics. So we have a couple of very useful commands. One is describe, which is showing the schema of a variable. So we can say, for example, describe sales data, and we will get the information about the schema. The second is dump. So as we are executing our programs, we can sprinkle dump statements in between. And as the program is running, we will see a fragment of our results shown on the screen. And that is very useful. As we are developing our programs, we would typically be writing a couple of lines of Pig. We will be using describe and the dump to make sure that the program so far behaves as we intended. And then we remove these statements and continue by writing more of the Pig code. Explain is something that will look familiar to developers with background in relational databases. We can have explain for SQL, and here in Pig we have the execution plan that is showing the logical, physical, and MapReduce plans. So you get the impression about the actual flow of the program. And finally, there is the illustrate, which is displaying a step-by-step execution of statements. It is using a fragment of data, and this is very convenient to get greater confidence that the program is executing properly. Now, these capabilities are particularly useful when we are writing our programs in local mode, So our turnaround times are going to be very fast in a matter of seconds, as opposed to minutes if we would be running our programs on a Hadoop cluster. And when we are confident that our program behaves as it should, then we are going to deploy it on Hadoop and try it out there. Let's see now a larger example of Pig code. In this example, we are going to look for top customers. And the overall idea of the program is the following. We would load some sales and customer data, and we are going to look for 3 best customers who are over 30 years old. We are going to list their ID and total sales, and we will store this information in HDFS. Here are some example data. For sales, we have the customer ID, the name, and the amount for the sale. We have a couple of records like this. Notice here that our top customer is going to be Mary Smith with total $2,100, and then there are a couple of other customers after that. Then we have some customers. We have the customer ID, the name, and the age. We have a couple of records. And the output data that we should get should look like this. So customer with the ID 1002, the total sales $2,100, and so on. The values are sorted in decreasing order. So let's see, how would we write a Pig program to achieve that? So the first thing that we will do is to load some data. So we are going to load the data from our file, and we are going to define the schema where we have the user ID, character array, name, and the sales amount. Then we are going to load the customers from another file, and we define the schema. So we have the ID, name, and age. The first thing that we are going to do is we are going to filter the customers who are over 30 years old. And you remember we said that doing projection early is one of the best practices because it will reduce the amount of data that we need to process. So in our example, we will first identify those customers who are over 30. The next thing is to do the join. So we are going to join customer's age. We are doing the join by ID, and we have join with the sales where we have a user ID. The result of that is join. And then we are going to group the joined by ID. So the result at this point, grouped, is going to be the ID, which is going to be followed by all the records that are joined. And then we will say, we are going to create the total. So we say for each group, generate, and you can see here example of positional notation. So we have a $0 that will indicate the very first field in the tuple, and then the next one is sum. $1 is going to be the next element, and then we are looking for the sale amount. You can imagine that there will be a whole set of different sale amounts, and they're all going to be summed, and we will call the result total sales. So at this point, we are going to have the user ID and the total sales. We are going to sort them in descending order. And then finally, we are going to say limit sorted 3. So we are looking for the top 3. And eventually, we are going to store the result into a file. So we say store top 3 into, and then the file location. Now, what will happen there is that in the execution in HDFS, a folder will be created that will contain the results. Normally, when you execute in MapReduce, the result is split to a number of smaller files. So the top customers that will contain our final result. Let's see now when to use Pig. Pig is great for parallel processing of simple data analysis tasks. So we see that it is really good for fairly easy programming with data flow sequences. One of the reasons why we decide to switch to Pig is when we see that it is rather difficult to write a single query in Hive. With Pig, we can build our program line by line. We can try it out, we can dump the value, we can describe our relations, and we can build our program out of small steps, and we can get confirmation on every step that the program is working as we expect. If you compare Pig with Java, you will see that we have a really high productivity in comparison with normal Java APIs. The code in Pig is often going to be about 20 times shorter than the code in Java, so great productivity. Of course, there will be some performance penalty. It is usually within 2 times in comparison with Java code, but it is worth it in almost all cases. To summarize, when do we like to use Pig? It is really great for ETL data pipelines. So the statements that we have, the data flow paradigm works really well for ETL. And it is also very useful for raw data processing. So if we can write our UDFs that will process the raw data that we have, Pig is a very suitable choice for that. And as we mentioned, iterative development line by line is one of the great reasons why people decide to use Pig. No solution is perfect, so Pig has some rough edges too. One of the reasons why you would feel that Pig is not such a great choice for your program is if you require iterations, if you require various complex control structures, you will see that Pig just does not provide them. Such applications exist. You will find them often in machine learning, you will find them in more complex applications, and you have to look for some other choices. Now, one possibility is you can write your UDFs, but when you are using Pig, your UDFs are going to be in a completely different language. They're going to be written either in Java or in Pig. So suddenly you need to switch the programming language environments. And in practice, it is often data practitioners who learn Pig and they are not that familiar with Java or Python. So that can be a problem. In such situations where your developers prefer SQL, you should consider Hive. There are many developers who actually switch between Pig and Hive, and we have seen projects where for some tasks developers choose Pig, and for some other tasks developers are happy with Hive. One technology to consider is Scalding. We said that Scalding is domain-specific language on top of Scala. It is a library, and you would use Scalding if you would like to benefit from the power of the full programming language, and that includes the complex data structures, all the computations that you can do with the regular language. And also, a solution like this, which is done in a real programming language, fits into the whole development process. You can do your test-driven development, unit testing, continuous integration, and so on. In this section, we will introduce Scalding, a Scala library for programming big data. In order to understand Scalding, we need to first take a look into Scala. Scala is a programming language. It is a full programming language that has the roots in both functional and object-oriented paradigm. It is a descendant of Java. It runs on JVM, and it can use all of the Java libraries. In fact, many programs are mixes of Scala and Java code. One of the nice things about Scala is that language is very expressive, and the applications need significantly less code than Java. Sometimes that can be 1/2, sometimes that is 1/5 of the Java code. One thing that is really interesting about Scala is that it has a functional background. What that means is that functions are first-class citizens in the language, and the functional paradigm is known to be very suitable for massively parallel computing. Now, why would we use Scala for big data? Well, first of all, in comparison with Pig and Hive, Scala is a full programming language, and that means that it will fit into our normal software development workflow. We can do our development starting with test-driven development, we have continuous integration, and we have all other benefits of full-blown programming languages. On the other hand, we also have a great productivity. The programs that we write in Scala tend to be significantly shorter than in other languages. And finally, this is a language that is compiled, it runs on JVM, and it has a very good performance. Performance of Scala programs are similar to those of Java programs. Now let's see what is Scalding. Scalding is a domain-specific language and a library for Scala, which allows us to program our MapReduce in a very easy way. The domain-specific language will be converted into MapReduce eventually. So you will have the same ultimate execution target as if you are programming in Java, only you will be significantly more productive in that work. The background of Scalding is that it was developed at Twitter, it is an open source project, and it has many notable users. So Scalding is often a choice of high-tech companies who are not afraid of using a real programming language for big data systems. Now let's see, how would we position Scalding? Well, first of all, we have a Hadoop as the background. Then we have Cascading. Cascading is a Java library, and on top of that, we have a Scalding. So Scalding will be compiled into Cascading, and the Cascading will eventually run on Hadoop. So what is this Cascading library? It is a high-level, very productive Java library for MapReduce, and it enables us to program using the data flow paradigm in Java. So we have taps, which are sources for our data. We have pipes that are carrying this data. We have various processing steps. We can describe what happens to this data which is being moved from one pipe to the other. And eventually we have sinks. Cascading provides for interfacing with many popular data sources, relational and NoSQL databases as well. In this video, we will see the basics of programming with Scalding. So let's do the obligatory program, the word count, and let's see how do we write it in Scalding. First, we have the import statement. We will be importing stuff from the Scalding libraries. The underscore at the end indicates that we are importing everything. Import statement has no consequence on the runtime. It is just something for the compiler. And then we say that we have a class word count job. We can pass some arguments, and we are saying that this class extends a job. The job is the superclass for the word count job and provides some common functionality. Then in the next line, we are indicating our source of data, which is the text line. It is a very primitive input mechanism, and we are passing the arguments with the value input as a string. So as we run our program, we will be passing the input and output defined as strings, and we will be opening HDFS files with these names. After the text line, we are indicating a flat map instruction. A flat map is going to take the line of input and it is going to create words. And the way how that works is that we are going to take each line of text and we are going to split it using a separator like space or new line and similar. So we are going to split the words. The meaning of flat map is that we will not just have a collection for each line and then the collection contains the words, but we are going to flatten it. So the end result is that we will have a collection of words in the whole file. The next line is group by. So we are grouping by the word. Then we are taking the size of that group. So basically, we will count how many words of the same kind we have. At the end, we are going to write the output. We are indicating that we will be writing in a TSV. TSV stands for tab separated values. It's one of the simplest data formats, and then we will be writing in the file that was indicated as output. This input and output are defined as strings that we will pass in as we are running our program. So as you can see, the program is fairly short, and for a Scala programmer, there are almost no surprises here. The program nearly feels as if you are using ordinary built-in collections from the standard Scala libraries. How do we run Scalding? Well, there are two modes. The first mode is local mode. Local mode is going to run on your machine. It is great for development. You have very fast turnaround times. And what we really like about it is that it enables us to do test-driven development. We can write our unit tests, we can try them out, and really we can improve the reliability of our programs. When we are done with development in the local mode, then we can deploy our programs on Hadoop. The nice thing is that we are deploying the jar file as we would do with completely ordinary Java programs. So from the point of view of MapReduce and Hadoop, there are no differences between the Scala program and the Java program. Scalding provides us with 3 APIs for dealing with big data. The most commonly used API is what is known as the field API. It is very easy to use. We are accessing fields in our files, and this API is untyped. So that means that compiler is not going to be able to check everything in our program. This is the oldest API. It is the most popular and very, very easy to use. The next API, which is growing in popularity, is the typed API. So we are indicating what are the types of columns in files that Scalding is accessing. The big benefit for us is that we are able to benefit from compiler checks, so we will be getting fewer errors at runtime. Now, this is something that is quite interesting for big data programs, because you would really prefer that you get error message from the compiler. Then, when you are running your program on Hadoop, maybe you are in the second or third hour of execution for very large data set, and then you get a runtime error. So ideally, we would try to get as many compiler errors and warnings during the compilation time before we really run our programs on big Hadoop cluster. And finally, Something new and unusual in these APIs is the metrics API. And this API allows us to work with big data metrics calculations. So the system is enabling us to deal with sparse matrices with huge dimensions. And this is something that we can do for graph processing, for machine learning, something that we cannot do with other tools for programming Hadoop. Now, for all of these APIs, one thing that is a big benefit is that the APIs look very similar to what an ordinary Scala developer already experienced when working with standard libraries for Scala. One of the benefits of Scalding is that it provides access to a variety of external stores. So it provides adapters for accessing relational databases and a variety of NoSQL stores. So we can access HBase, which is the real-time database that runs on top of Hadoop, Apache Cassandra, a NoSQL database of the columnar type, MongoDB, a popular document store, and that improves our productivity because we can tie in various sources in our programs, and you can achieve a mix of big data on Hadoop combined with a variety of other stores. In this video, we will discuss when to use Scalding. So, when to use Scalding? Well, the first reason why would you like to use Scalding is to benefit from the power of a full programming language, as opposed to Pig and Hive, which are somewhat limited in what they can do. The other reason why would you like to use Scalding is to fit into the ordinary software development lifecycle. So we have test-driven development, we have continuous integration, we have all the usual things. The next benefit is that the code that we are writing with Scalding is rather short, and it is easy to understand. The intent of the program is easy to deduce from the code. Sometimes the organizations may start with Hive and Pig, and they recognize they don't have all the support that they need to write more complex big data programs. For example, if you need to do some machine learning algorithms, you often have to do iteration, and this is something that is very difficult to do in Hive or Pig, or you have to even escape their boundaries and use some command shell scripts to run programs in multiple iterations. In Scalding, you can do that naturally. You would just use a loop in Scala and program it in that way. Scalding is going to be a good match if you have big data developers who are not afraid of real programming language. And this can be a factor. Depending on your organization, big data developers could be coming from the database background where they might be familiar with SQL, but they could be challenged to program in real programming languages. And one of the reasons to use Scalding is to attract top developers, to use cool state-of-the-art technologies. And we have seen that already with Scala. It is not absolutely necessary to use Scala to achieve the functionality of their products. But with Scala, which is a very hot, advanced language with great productivity, you often get better developers to sign up for your team. There are situations where Scala is not the ideal choice. Imagine that you are doing work in the organization where the only thing that you do is very basic ETL. The developers that you have don't have the background in programming, so they would like to stick to something that is rather simple. In that case, Hive or Pig could be a better choice. Sometimes the big data developer culture that you have does not welcome programming. Again, this is related to the background of the people that you have. And you need to consider that the Scala, which is necessary in order to use Scalding, is a powerful but a complex language. It is a very rich language, and you cannot learn it overnight. So learning Scala could be too challenging without proper training or a guidance. In these situations, we would prefer to stick with Hive or Pig and use Scalding on more complex projects. In this section, we will explore the Hadoop ecosystem. Hadoop ecosystem evolved over the last couple of years. The foundation of Hadoop is HDFS, Hadoop Distributed File System. On top of that, modern Hadoop runs Yarn, yet another resource negotiator. And on top of Yarn, we have a variety of systems. We have a Pig and Hive that we have explored in previous sections that enabled us to productively work with Hadoop and program MapReduce tasks. There is a Tez, which is a new execution engine that provides better performance, mostly by eliminating unnecessary reads and writes on the disk. HBase is a real-time database that runs on top of Hadoop. It provides good performance, dealing with very large volumes of data, and it enables us to deal with updates of various data, something that we know is not directly possible in plain Hadoop. Zookeeper is a part of Hadoop infrastructure that is dealing with management of clusters. Scoop and Flume are important tools for integration with other parts of industrial IT. Scoop is enabling us to interact with relational databases. Typically, we would do import and export. And the Flume provides for transfer of data from various machines and sources into the HDFS. After that, we have a set of newcomers: Storm, Spark, and Flink. Storm provides for stream processing of data in real time, while Spark and Flink are new architecture that can be used together with Hadoop, and they provide the improved performance, particularly by utilizing in-memory computing. The Hadoop ecosystem is growing, and you will see many new members that are joining the Hadoop ecosystem. So to summarize, with Hadoop ecosystem, we have a growing set of projects and technologies, and one of the major thrusts today, which we see with Spark, Flink, and Storm, is moving beyond batch processing that characterizes the traditional Hadoop, particularly by using the in-memory computing and stream processing. Apache Tez is the API and framework that provides us for better execution time of our Hadoop programs. It runs on top of Yarn, and what it does is organize MapReduce into directed acyclic graph of tasks. And it is used by systems like Pig and Hive. One of the interesting things that it can do for us, it can dynamically reconfigure the execution graph and so optimize our programs. Now, the effect for our Pig and Hive programs is that we don't need to wait so long as with conventional Hadoop. So Pig and Hive become more and more interactive. Great performance improvement. And the question is how easy it is to switch to using Tez. Well, the answer is it is very easy. We just need to set the configuration that we are using. For example, in Hive, set Hive execution engine is Tez. And that is all that we need to do. So great improvement and big benefits when it comes to performance. Performance is the key gain of using Tez, but also there are a couple of others. Better predictability, so we can foresee better and estimate what is going to be the execution time for our tasks. We have fewer delays and overhead. We can utilize our resources, our machines on which we are running the Hadoop better. And one of the great benefits is significantly reduce load on HDFS. What Tez can do is to eliminate unnecessary writes and reads from the disk. So when you have different parts of your MapReduce jobs, normally they would have to write their intermediate values on the disk, and then the next part will have to read from it. With Tez, they can directly pass these values to each other. And the other benefit is that we have a reduced network usage. So overall, we see not only the improvement in execution time of our programs, but we also have a better programmer productivity because you need to spend less time optimizing Hadoop programs. And also, when you're doing iterative development, when you're trying out, your execution time with Tez is going to be faster. So you will be spending less time working on your development. HCatalog is a centralized metadata service. If you remember, in our sections on Hive and Pig, we have seen that in both cases, we could define the schema for the data that we are reading. In Hive, we will be providing definition of the table, and then in Pig, we will be defining the schema for reading of our relations. Now, you could imagine that we have the same file, and you can process it with both Hive and Pig. Without HCatalog, you would need to define this metadata in both of these programs. So one of the nice things about HCatalog is that we can store this information about the schema, and then we can reuse this information from Pig, Hive, and other programs. So basically, HCatalog will operate like a database, and it will provide us with storage of our metadata. It can help us by streamlining the work. Mahout is the library for machine learning, and it includes a variety of algorithms. Now, the key thing here is that we are dealing with scalable machine learning. So it is machine learning on the Hadoop scale. Mahout introduces the traditional machine learning features. There is a classification, there is clustering of different items based on some similarity function, and there are also libraries for implementing various types of recommenders, user-based, item-based, and so on. Machine learning is one of the more and more popular features in big data processing. Integration with other systems is extremely important. And primarily, we are going to talk here about integration with relational databases. Scoop is a tool for automated database import and export, and it is bringing together the relational databases, some NoSQL databases, and Hadoop. Database metadata is used for definition of structures, and one of the nice things about Scoop is that the Scoop is transferring data in parallel, so it achieves better performance than if you are just unloading and loading the data into our systems. So Scoop focus is relational database. Flume, on the other hand, is a distributed streaming tool that can help us when we need to integrate with non-relational kinds of data. For example, various logs, message queues, web services, and similar. So it is a horizontally scalable system for integration. We can also tune what is going to be the reliability, so we can provide the appropriate trade-off between reliability and performance. We can implement both push and pull for our sources. And one of the great things about Flume is that it integrates with a variety of different data sources. So we can deal with files, we can deal with output of programs, logs, message queuing protocols, and so on. And the outputs can be in HDFS or HBase, and the number of data outputs is also growing. One of the things that you could also do with Flume is to introduce decorators. So as the data is being transferred between the parties, you could actually process it and do something with it. When we are working with Hadoop systems, we will be working with clusters of machines. Managing clusters of computers is always a challenging task, and the Zookeeper is the distributed coordination service that we will use for that purpose. So Zookeeper internally uses a shared hierarchical namespace of data registers. It provides for loose coupling, fault tolerance, so it has automatic failover, and it uses majority voting for making decisions. It is a fast system because all the data is read from the memory, and it is a very widespread system. So many modern distributed technologies, even besides Hadoop, are depending on it. The common uses for Zookeeper are the configuration management of our cluster. It is dealing with providing information who is available, what machines can be used for our computing. It provides for distributed synchronization, also naming service, and also dealing with challenges like rebalancing the clusters, leader election, and overall it provides a simple but highly reliable data registry. And as we mentioned, it is a very widespread part of the Hadoop. Now it's a standalone project used in many distributed applications. In this section, we will introduce HBase. Let's see what is HBase. HBase is the columnar database that runs on top of Hadoop. It is a distributed database, so data is stored on many machines that we have in the Hadoop cluster, and the data structure that is fundamental for it is something that is called a sorted map. This database has a very flexible schema, so the columns that we have for our tables can be dynamically added on the fly, and the number of columns that we can have goes into billions. So it's a very different architecture than what we have with relational databases. This type of design is often called a wide table or a long row database. One of the great advantages of HBase is that it is a system that is horizontally scalable. It can be spread over hundreds or thousands of machines. And one of the other characteristics is that the data that we have can be sparse, and the HBase can very efficiently store this type of data. Looking into some other characteristics, is that it provides strongly consistent reads and writes. It is also a fault-tolerant system, so that one machine that is part of the cluster that is running HBase, the machine can die, and this is not going to prevent us from running computation. So data is stored in the fault-tolerant fashion. Naturally, you will see that when you talk about systems like HBase, which is a representative of NoSQL systems, you will find that the systems that scale very well need to sacrifice some of the other characteristics. And in many cases, what is sacrificed are transactions. So transactions are limited. Transactions in HBase would work for a single row only. But the advantages are such that HBase can handle data in a range of several petabytes, and it provides excellent performance of millions of queries per second. HBase has its origin in Google technologies, particularly in the system called Big Table that was described in a paper in 2006. Google has its own internal implementation, and the HBase follows these ideas and implements them in Java on top of Hadoop. Some of the features of HBase is that it is built on top of HDFS, and as various other columnar stores, it provides for very good compression. It also can deal with in-memory column families, and that provides us with significantly improved speed if our data can fit into the memory. Some of the other interesting design choices, inclusion of so-called Bloom filters, which is an approach that can provide us with a very quick resolution if an element is member of a set or not. We have also features for bulk loading. Zookeeper, the system that we have seen in previous section, is acting as the coordinator for the cluster. And we can involve HBase tables as input and output for various MapReduce jobs. So you can see that HBase has a great set of advantages over traditional Hadoop and the MapReduce that we would run on it. Let's see how we would run and use HBase. During development, you would typically run HBase in a local mode. This will enable you to have really good response times, convenient for the development, and then later you can deploy it on the cluster. You have a command language interface. Primarily, you will be using Hive from APIs that exist in various languages. They tend to be fairly low level, they're rather primitive. HBase on its own does not provide any query language. But there is a set of projects that are including HBase and SQL and putting them together. One notable project is Apache Phoenix that is giving us SQL on top of HBase. Let's see what is the HBase data model. We have the concept of so-called column family. That is close to table that we have in relational database. The data structure is a sparse, multidimensional map. And the model is such that we have a triple of a row and column. You can think of those as coordinates. And in addition to that, there is a timestamp. This is something that we call a cell. And that is interesting that we are storing the timestamp. That gives us possibilities to run queries in which we can ask, how did the data look like at a particular point in time? Then we have regions, which are contiguous sets of lexicographically sorted rows. They are basically representing a unit of scalability in the system. We mentioned that systems like HBase often do some trade-offs, and one of the trade-offs in many of the NoSQL distributed stores is that don't have joins, so HBase belongs to this category. Now the question is then, so how are you going to use such a system if you don't have joins? Well, the common workaround or even a recommended approach is to denormalize everything. And it is perfectly acceptable in such designs to store data in multiple places. Remember that the primary enemy that you are fighting here is lack of performance for very large data sets. So we will be willing to sacrifice the efficiency of storage, have our data stored multiple times, but then when we need to access this data, we will be able just to go there and read it without doing any joins at the read time. And naturally, this will require you to be very careful when you are designing your schemas. So one of the typical things that you would do for a model like this is that you would decide what should be the queries that will be running over this database, and then you design your data model that everything that you need to answer a particular query is stored in one table. So you just need to go and read. You try to avoid doing any additional work at runtime. Anything besides read is not considered to improve your performance. And we have mentioned that there is this data structure called Bloom filters that provides us with very quick responses for misses. So if the key is not in the system, we hear about that very, very quickly. Tables and rows. A table can naturally have many rows. Each row has a primary key, and HBase is not choosy about your keys and data in general. So a key is just a sequence of bytes. For a row, we can have an arbitrary number of columns, and a column is also just a sequence of bytes. So you can see HBase does not have any notion of data structures or primitive types. Everything is just a sequence of bytes. And internally, the rows are sorted. All the data is versioned and timestamped. Column families are providing us to organize our columns, and they would be similar to things like records and objects. Basically, one column family is going to provide us for a unit of access, and we don't need to access or load the data that is not used. So basically what we do here, we are minimizing the data movement, and we can design our system so that the related things go into the same column family, and that will give us performance advantage. And then the other things that you can do with the column family is you can define various settings like compression, version retention policy, or cache priority. Regions are subsets of rows. They will be automatically sharded, and they would be acting similar to range partitions. So they enabled us to also more efficiently design our system. The API that we have for HBase is rather simple, and normally we would use it from Java programs. And it provides a fairly low-level operations like get, put, delete. We can scan for values, increment column value, and we have also MapReduce as a source and sink for our data. So fairly low-level API, you would typically use them from the Java programs, but you should also consider looking into Apache Phoenix that provides us with an access from SQL, and normally in programs then you could be using a JDBC to access the HBase data. Let's see when to use HBase. HBase is going to be a good choice when we need to deal with large amounts of data. So data over petabytes of size is a good match for HBase as a database. We would use HBase when the data model is simple and when the access pattern is known in advance. We talked earlier about the design of data for HBase, where you would like to have data in a denormalized form. So when you're running a query, all of the data that is needed for the response is in one place. One of the advantages of HBase is that the schema does not need to be fixed, so we can be adding columns dynamically in our application. Comparing HBase with MapReduce on Hadoop system gives us random reads and writes. And what is interesting is that they can be done in a very high-speed fashion, and we can run millions of queries per second. When not to use HBase? If you imagine that you are going to have tables and that you will be doing joins, then HBase is not going to be a good choice. Also, if you're dealing with small amounts of data, you may be better by using an ordinary relational database. Sometimes you see that the low-level API that you have in HBase is not sufficient for your operations. Sometimes you think that you can be using Hive, and it is interesting that if you run Hive on top of HBase, you are going to get a relatively poor performance, worse than with Hive. So if your random access is not something that you need, Hive over plain HDFS can be better. Now, HBase belongs to the category of Columnar Stores, and it is not the only Columnar Stores that we have. So sometimes you see that the HBase is one of the possible candidates, but not necessarily the only choice. You should consider Apache Cassandra. Apache Cassandra has many similar features to HBase. It is a peer-to-peer shared nothing architecture, and it provides a SQL-like query language. So we often recommend, when Cassandra is an option, check out HBase and vice versa. In this section, we will explore the two newcomers to Hadoop. These are the Apache Spark and Apache Flink. If you look in the history of Hadoop improvements, we can see that in the beginning we started with plain MapReduce. MapReduce is a rather brute force algorithm, and it is not necessarily the most optimal way to run things. One of the common disadvantages of MapReduce algorithm in its traditional implementation is that it is very I/O heavy. So it would be writing the data on the disk, and then this data will be read again by the subsequent tasks. Apache Tez introduces an optimization mechanism where we don't need to have that many inputs and outputs, but the data can be directly streamed to the next stages in the processing. Tez introduced significant advantages to the processing time, and it made Hadoop moving slowly from the batch into the near real-time execution. The ideas behind MapReduce are relatively old, and a couple of years after they have been introduced, scientists have been working on a couple of alternative mechanisms that are not necessarily using MapReduce. Also, MapReduce did not use a vast amount of knowledge that you accumulated in the area of relational database design, particularly distributed relational databases. So we have two systems that are building on a more optimized, more streamlined foundation. One of them is Apache Spark, which is trying to move more data processing into memory, and the other one is Apache Flink. Currently, Spark and Flink have a number of commonalities, and we are going to treat them both as the new generation of Hadoop systems. Let's see first the key element of Apache Spark. So the important features there is that Spark is trying to use in-memory data structures. And the data structure that is used for that purpose is something that is called a resilient distributed data set. And why are they resilient? Because if the failure occurs, the data set can rebuild itself. So basically you have some trace how this data set in memory is constructed, and you can rebuild it based on your actual data source. Spark is coming with a rich set of operators. Many of these operators are inherited from the design of Scala collection libraries, and the programs that you are writing in Spark will remind you very much to programs that you would write in Scala as if you are dealing with in-memory data collections. Spark is a rather efficient system, so we have seen really good numbers, 10 to 100 times in memory faster than Hadoop MapReduce. Also, the Scala API is very productive, so we have significantly fewer lines of code, 2 to 5 times less code than if you are using rich APIs in Java, for example. The key components of Spark are the following. At the bottom, we have the Spark core engine, and then we have a number of systems on top of that. So we have a Spark SQL that is adding conventional SQL capabilities to Spark. This is going to broaden the appeal of Spark. There is the streaming API, which is combining the batch and streaming processing. So the code that we are writing for both batch and streaming is very, very similar. Then there are machine learning libraries. There are libraries for dealing with graphs. And there is also Spark R that provides the R programming language interface to the Spark. At the time of creating this course, some of these different components were at a different level of maturity. Some of them are industrial strengths, while some of them were in early development. Internally, one of the interesting elements in Spark is the data sharing, which can be happening so that we begin with our data in HDFS, we are executing some code, we are providing some processing in iterations, and we have some result, which is held in the memory of the machines in the cluster. Then we will be processing this data in the second iteration, and then we have the results of that stage in processing again held in memory. And this data in memory can be used to answer various queries. So as you can see, it's a very efficient mechanism which is reducing the I/O and are trying to answer various queries from the data in memory. Apache Flink is the new system in Apache Hadoop ecosystem. And one of the interesting features of Apache Flink is that the programs are compiled into plans. And these plans are then optimized and then eventually executed. So if you're coming from a relational database background, you will say, well, this is nothing new. We have been seeing that in relational databases. There are access path builders, and then there are query optimizers. And now we are gaining the benefits of this type of execution in our Hadoop and big data systems. Flink is a result of a European research project, and it has a couple of goals. First, very high performance, then unification of batch and streaming into a hybrid runtime, and finally, simplicity for the developer. Spark and Flink have many common points when it comes to programming, and ideally you would be using Scala, very expressive language. Few lines of code will accomplish a lot in this setting. Internal data structure of Flink is called the dataset, and it is similar to RDD that we have in Spark. It can be produced or recovered in a number of transparent ways, like using in-memory collections, like an RDD. Sometimes it does not need to be materialized at all, and sometimes it is updated in an iteration. So the optimizations that we have in Flink is that the optimizer selects an execution plan, similarly to what we have in a relational database, and then the system is going to optimize, and it can use the size of the input files for that. When we are running Flink, we can run it as a standalone installation over our cluster, or we can run it on top of Hadoop. That is convenient because now you can use Flink on top of HDFS. And both Spark and Flink are providing integration with many of the existing Hadoop technologies. To summarize the features and advantages of these systems, they are providing us with ability to run iterative algorithms and do that in a very efficient way. Both systems are dealing with very good caching, and they reduce the overhead in comparison with conventional Hadoop. Both systems are unifying batch and stream computing, and both of them favor Scala as a natural expressive language for big data processing. And there is also support for other languages. Particularly, SQL is of interest there, as it will be able to address much larger data processing audiences. One of the things that I would advise you to be careful is to watch out for less mature components. Both of the systems are having areas that are relatively new, and you need to watch if you are going to use them for production. In this section, we will explore NoSQL stores. The first question that we may have is, so what is NoSQL? You should understand NoSQL as not only SQL. It is a bit unfortunate name. You should better think of it as non-relational data stores. The reason is that some of these NoSQL stores actually have some version of SQL. These NoSQL stores have been created with the goal to address deficiencies of relational databases, and the NoSQL is an umbrella name for a variety of different technologies and approaches. One common thing is that they are non-relational, and they are typically distributed data stores. Some of them are capable of executing MapReduce jobs, so they can spread the processing over a number of machines, and that they are addressing the batch problem of plain Hadoop. So these databases will give us answers in real time. So let's imagine now that we are dealing with the world of relational databases. We can see that we are having great advances in capacity of disks and also in processors. Our CPUs are not getting that much faster, but we are able to deploy a larger number of them. And the processing power and the storage capacity is somewhat behaving linearly. So if I need 4 terabyte disk space, I would pay 2 times more than for the 2 terabyte hard drive space. So we have a fairly linear growth. Now, if you look into the relational databases, we see that it is relatively easy to start with smaller systems, but then as our appetite is growing, the cost that we have for relational databases is increasing. So we can say that when we are dealing with very large volumes, dealing with relational databases is going to be rather expensive and the performance is dropping. And we are also dealing with web scale problems where these volumes are simply out of reach of relational databases. So what we are trying to do with the NoSQL solutions are two things. First, we would like to get a linear response for the cost and performance of the system. And we would also like to allow for unlimited volume growth. We have seen that the unlimited volume growth was one of the primary goals for Apache Hadoop that we have explored in previous sections, and we are going to see how do we address the real-time capabilities with NoSQL stores. When it comes to processing, we have two approaches. One is the scale-up approach, which is commonly used with relational databases. In this approach, when you need more capability, you are getting a bigger and bigger computer. In the scale-out approach, you are running on relatively inexpensive machines, but you are going to use more of them. It turns out that scaling out is the optimal choice for growing our systems, and scaling out is the common approach that is used in a variety of the NoSQL systems, and we have seen that Hadoop is using the same approach. Typical NoSQL systems come in a variety of flavors, but they have common capabilities. So they tend to be non-relational systems. Most of them are distributed, they are horizontally scalable, and usually they don't need a fixed schema. You will find that you have a set of established players. There are always newcomers coming, so I recommend you to check every 6 months. There will be somebody new in the game offering some of the interesting new characteristics. And for many of these systems, you can say that they are specialized for a particular role, and you may choose among many systems with related capabilities. As we mentioned, many of these systems are running in a distributed environment, and there is something called the CAP theorem that describes the behavior of such systems. The CAP theorem is saying that at most 2 of the following 3 may be satisfied, and that are consistency, availability, and partition tolerance. And this theorem was established in 2000, proven in 2002, And think about our conventional systems. For example, relational databases don't have partition tolerance, but they have consistency and they are available. When we are working in a distributed setting, we are typically choosing the solution which is the eventual consistency. What that means is that in a distributed database, a value would need to be written at multiple locations to provide for fault tolerance. So we need to have multiple copies of data that will exist on multiple machines. And here we are facing two design choices. One choice is to lock the whole system until all nodes confirm that the data is written. We will be locking a set of machines in a distributed environment. We are going to have a rather poor performance that will not be acceptable to our users. The common choice is to allow reads to reflect values that are not necessarily the latest. So you may be returning some values that are somewhat stale, and we hope that this is going to be okay with our users. Now, when we say eventual consistency, that does not mean days or weeks. Eventually typically means milliseconds. But one of the big benefits is that our system is available and we are able to provide some response to the users. NoSQL stores come in several flavors. When we are working with a store, we need to choose a store that is going to be a good match for our application. Sometimes we are going to use several different stores that we may be using together, and this is something called Polyglot Persistence. There are four major flavors of these stores. We have a column family store. We have actually seen one of these as Apache HBase, which is running on top of Hadoop. The values are stored in columns, and the systems are good for storing sparse data. We have a document-oriented databases. Typically today, they will be storing data in JSON format or XML. Then we have a key value stores that act basically as distributed hash tables. And we have graph databases that can provide for representation of very complex data models containing relationships between many nodes. When we are selecting a database for our application, we need to think about the compromise between the scale and the complexity of data. So if we put these two as axes of our coordinate system, we see that key value stores can achieve the highest scalability. Apache Hadoop that we have seen earlier is an example of key value stores, but there are also stores that are specialized for non-batch, near real-time and real-time capabilities. We have column family stores. They don't scale as much as key value stores, but they are dealing with a more complex data model. Then we have a document-oriented stores. The data models that we can store in JSON or XML are significantly more complex than what we can do with column families, but we don't scale as much. And then finally, we have graph databases, which typically don't scale as well as the other systems, but they can provide us with the most complex data model. The question is, what are the requirements of your application? You will find that if your data needs are not that extreme, you could use any of these systems to power most of your application. If you raise this bar, then you will see that you need to choose one or the other system, sometimes working together with alternative architecture to cover all the needs of your application. Let's see now the key value stores. Key value stores have a simple data model. It consists of a mapping between the key and value. You can think of them as a large persistent maps or hash tables. And the values that we have can be lists, they can be hashes. Usually such stores don't have particular preference what is the value, so we have a lot of flexibility. Their APIs tend to be simple and they tend to be very easy to use. Because of their simple data model, they can also scale very well. On the other hand, because of the simplicity of the data model may be too simple for most applications, and you may want to look into some of the alternatives, perhaps the columnar or the document or perhaps even the graph database. There is a set of systems that are quite popular in this area. You can see them here. And in general, you would be using key value stores for simple data models and when the scalability is essential. Let's see some typical use cases. The common thing for all of them is the data model is simple. And one of the very common choices is to have a JSON for the value. And you could imagine a couple of typical uses for such systems. Storing session data of web applications is a very popular use case. Instead of storing the session data on the web server, we will externalize it and store it into the key value store. What we achieve by doing a design like this is that the state of the user interaction is not tied to the web server anymore. And that means that the subsequent user request can be served by any of the web servers that will then reach to the key value store to retrieve the state. And this is one of the very common ways to increase the scalability of web applications. Another use case is to store user preferences and profiles. Usually they have a fairly simple information, and key value store could be perfectly adequate for something like that. Dealing with data with shopping carts is another popular example. You can imagine that the key can be some user ID, and then the value is the serialized content of the shopping cart. When you are thinking about key value stores, you may find that different architecture of NoSQL store could be good enough solution, adding you additional advantages of dealing with more complex data model. When you are facing a dilemma which store to use, you could use some performance or scalability tests and see if a different architecture could actually handle your load. If yes, great, you will be able to deal with more powerful data store. If not, you may actually decide to choose key value store only for particular parts of your application, those that require true scalability that will be supported by a key value architecture. Let's see now the columnar stores. The key data organization of these data stores follow the column family model. Column family is going to remind you to a table in a relational database, but there are some differences. The table is sparse, and the underlying data model is a mapping from key to multiple pairs of columns and values. Usually stores like this do not care what is a key, what is a column, or what is a value. And we are able to give columns names, and we can do that dynamically. The names can be practically anything. You could often use, for example, timestamps as the names of the columns, and you can have your data models organized in something that is called a long row. So you can imagine, for example, interactions with the customer where you have a key, which is the customer ID, and then you have the column, which is a timestamp, and the value represents the interaction with the customer. And every time when there is an interaction with the customer, you're going to add another pair of the column and the value. Systems like this have more functionality than a key value stores. So we can index column families, but usually it is recommended not to do that and follow the simplest model for our application. We can store complex data, and the rule there is to denormalize. It is accepted that it is perfectly okay to store a piece of data in multiple places. And this is all done in order to improve the retrieval speed of our data. So when you are thinking about the design for your application, you should know what are the queries that you will be having, and then you would organize your column families so that all data that is needed can be accessible without doing any joins. Here you can see some of the most popular systems in this space. One of the systems that we have already seen is HBase, which is the column family database. It's a part of Hadoop. Another Apache project, Apache Cassandra, is very similar in many regards. It is a peer-to-peer system which does not have any single point of failure. And one of the very attractive capabilities of that system is that it has automatic replication even across data centers. And that this capability is there from the origins of the system and not something that was added retroactively. Column family is going to be a good choice where we need great scalability, fault tolerance, and our data model is more complex than what we have with key value stores. The typical use cases for systems like this would include high insert volumes, for example, logging, time series applications, dealing with real-time updates. Many of these systems can expire the content automatically. So for example, when the data gets older than 2 months, you can expire it automatically from the system. Cross data center replication, particularly for systems like Apache Cassandra. And most of these systems would allow you to run MapReduce analytics over the stored data. So merging the capabilities of Hadoop with the NoSQL stores. One of the drawbacks of systems like this, especially if you compare it with traditional relational databases, is that you don't have conventional ACID transactions. Document stores store data which is typically in format like JSON, binary JSON called Bison, or XML. The common trait for stores like this is that they typically don't need any schema, and you can store different pieces of data, which we call documents, in such a store without predefining what is the overall structure of such documents. In systems like this, you can use indexes to improve performance, and systems like this provide for the easiest transition from relational database systems. Usually, systems like this are quite optimized for ease of use. Their APIs are quite easy to use. In many cases, the API is actually implemented in JavaScript, and you are writing queries in JavaScript to access such systems. You can see here some of the popular systems, and you would be using document stores when your data is in some semi-structured form. Often, one of the application cases is when the structure of data changes through the lifetime of application. And that is very convenient when you start an application and you are evolving the functionality. So the data that you are storing in the beginning can look differently from the data that you are storing later after some time in the life cycle of the application. Document stores are often seen in web applications, and in such applications, they replace relational databases. Let's see now the typical use cases for such systems. You will find systems like this can be used for logging, especially where the content is variable. You're going to find them very useful for storing product information in e-commerce systems, particularly where the structure of product information varies from one product to another. Customer information is also a very good choice, particularly when you have some special information that you may attach to a particular customer, but it is not something that would require you to define schema and add this additional property for all customers. Content management is another good use case for document stores. And in general, data that has format that varies over time is a very good match. So having a flexible schema or no schema at all is one of the great situations for using the document stores. Web analytics is another use case. So we can summarize, great flexibility in structure of data is one of the attractive capabilities of document stores. Graph stores. Graph stores are storing nodes which can typically have some properties, and these nodes are connected through relationships. Now, these models with nodes and relationships can grow to be very complex, as in the case of, for example, social networks, product configurations, and similar. So the systems that store graph information are optimized for running various queries over such graph models. Some of the systems would introduce their own special query languages. Some of the others will modify SQL for reasoning over graphs. Some of them use some of the semantic technologies like RDFs and Sparkle, which is the query language for RDFs. Here are some of the common systems in this space. This space is very attractive, and we see that almost every day there is a new system in this space. In industry, we still don't see that many applications of these systems, but they are really excellent technical choice when the data is a graph, particularly when we are dealing with complex graphs. Typical use cases of graph stores are dealing with highly interconnected data. For example, working with social graphs, working with party relationships in an enterprise. For example, master data management for customers, suppliers, distributors, manufacturers would be a very good example. Location-based services are another example of use of the graph database. And one of the most frequent applications in e-commerce is dealing with purchasing analytics and particularly creating recommendations. One of the easiest recommendations algorithms would look into social graphs. For example, you could look into who are my friends, what are they buying, and then recommend such products to me. And such applications and recommendations algorithms can be very nicely implemented using graph stores. Now, in applications, we often see that graph stores are commonly combined with other systems. So you may have another database that is storing bulk of the data, and the graph database is just handling the relationships. But we also see the emergence of some hybrid models where you have nodes that behave like documents, and such databases provide hybrid access to document and graph functionality. If you don't have a hybrid database, then the graph database can focus on relationships, and you can have another database that will store the data. Data modeling for NoSQL stores. Traditional database development will start by creating some logical and then physical data models. Most NoSQL systems do not have joins, and that will result in a different approach to models. The most common approach is to embed the data. Basically, we are dealing with highly denormalized models with the idea that everything is oriented towards high retrieval speed of our data. And that would mean that a piece of data may be stored in several different places in our system, but when we are retrieving the data, we can just grab everything that is needed to answer the particular query. So we are dealing here with the trade-off that data replication is often accepted as a normal thing, and the benefit is that we are getting higher read speeds. If you think, why is that the case? We see that response time of applications is critical for the success and a good experience of our users. And even reads that are slowing down our response time in a matter of hundreds of milliseconds are often viewed unacceptable by modern standards. One of the anti-patterns that we often see when we examine the databases that are too slow is when we have a conventional relational database developer who carries the knowledge from relational databases into NoSQL and start organizing the tables as they would do in a relational way. Normalized data models using references are typically going to result in very poor performance of the systems. That is the most important anti-pattern. Normalized data models are very flexible, and in a relational database, they can be used by running queries that we didn't know about during the design of the system. The problem is that joins will result in poor performance. Think about that most of the NoSQL systems do not have real joins, and that means that we often see joins being done as application joins in our programs, and they would have just terrible performance. Now, graph databases are a little bit different. Graph databases can follow links in a graph without necessarily performing joins. So you may have the normalized data model in the graph database, and you can still achieve good performance. Different systems use different implementation strategies, and I would highly recommend that you run benchmarks as you are developing to make sure that your normalized model in a graph setting would have adequate performance. If you are dealing with non-graph-oriented database, denormalization is the common approach, and normalized data models are usually going to cause performance problems. We can see that the NoSQL is really not a perfect solution. We are going to trade off certain characteristics. For example, the flexibility and usability of the normalized data model, which would allow us to run different queries, even queries that we did not create during the development of the system. In the NoSQL world, this is typically different. We are going to design our data model so that we can answer the queries without performing joins. You should always remember that NoSQL stores vary, even within the same category. In order to create the data models that are going to provide optimal benefits, you need to be aware of the internal organization of the data within your particular data store. In this section, we will introduce streaming. How do we work with streaming data? Well, let's compare that with conventional processing of data, where the data is static. When processing static data, we have the data that resides in the database. We are providing queries to the system, and we are getting the results. Systems that are dealing with streaming data turn this around. We define a set of queries, and then we are passing data over the set of queries, and we are getting the results. The queries operate on some window of data, which is typically relatively small. It contains some fragment of data within a certain time period, which can be measured in seconds, minutes, hours, days, but usually not a very long period. When we look into the uses of streaming, we can say that candidates are those applications that need to provide a real-time or near real-time advice based on the current set of data. And you can see here a whole range of applications that are applicable in various domains, from e-commerce to monitoring, processing of logs, providing real-time recommendations, what products would be of interest, and similar. There is a range of stream processing systems, and here are some of the popular projects. Apache Storm is one of the most established projects for streaming. It originates from Twitter, and we are going to explore it in a bit more detail. Apache Spark, that we have already seen as a part of the Hadoop ecosystem, provides streaming functionality by dealing with micro batches. The input is being divided into smaller batches, which are then processed. Apache Flink, a system that is somewhat similar to Spark, also embraces the stream processing as the first-class citizen in their ecosystem. And we have a couple of other systems like Apache S4, which was originally developed at Yahoo. In the next section, we will explore the Storm stream processing system. In this section, we will introduce Apache Storm. Let's compare first Storm and Hadoop. First of all, Storm and Hadoop do not compete with each other, they complement each other. We will find several common characteristics. First, both of them run on clusters, both have master and worker nodes, and both of them use Zookeeper for cluster management. Now, Hadoop and Storm will differ in the following areas. Hadoop is oriented towards batch processing of large files that are stored on HDFS, and when you run a job on Hadoop, it will run to its completion. On the other hand, Storm will process the data in real time as the data comes into the system. The jobs run forever and they process the data that come in. Conceptually, Storm systems consist of spouts and bolts that have a particular set of functions. So let's see what they are. Spouts are sources of streams. Bolts would consume the streams and they would be emitting tuples. This whole thing together is called the topology. The flows of data between the bolts or between the spouts and the bolts are called streams, and they are unbound sequence of tuples. And tuples are lists of key and value pairs. Physical organization of Storm cluster is also interesting. We have a number of parts here. On the left-hand side, everything begins with Nimbus, which is the master daemon process. It distributes the code, it assigns the task, and monitors failures. We already mentioned that Storm uses a Zookeeper for cluster organization. The operational state of the cluster is stored on Zookeeper. Within a Zookeeper, we have a number of supervisors, and a supervisor is a daemon that is listening for work. The supervisor will organize the work of a worker process. A worker process will consist of a Java process that executes a part of this topology, and this worker process will use Java threads, we call them executors, to eventually execute the tasks, which are component instances that are doing the processing. Besides the relatively low-level API with spouts and bolts, Storm introduces a new API, which is at a higher level of abstraction. It is called Trident. It is providing us with stateful, incremental processing on top of a persistence store, and it is based on Storm primitives. Here you will find the usual operations for data: joins and merges, aggregations, groupings, functions, and various filters. If we compare core and the Trident, we see that the core supports spouts and bolts. One message at a time is processed, we have a low latency, and we work on tuple of streams. With Trident, we are working with streams of data and operations on this stream, and the processing is organized in micro batches. We have a high throughput, and we work on streams of tuple batches and partitions. Several best practices of Storm. One thing that you may be tempted to use is a guaranteed delivery. If you do that, you may cause some performance degradation, so you need to be careful. You always want to monitor your applications. As you are writing code for your bolts, you would like to unit test that code. And usually we will be using various mocking frameworks and techniques to provide substitute for the other parts of the system or for the functionality that is not implemented yet. You should always integrate with conventional systems, and considering productivity, you should consider Trident. Let's see now the key elements of Apache Spark and Apache Flink streaming. Apache Spark streaming is designed to be fault-tolerant, efficient, have a simple programming model, and integrate with batch and interactive processing. The idea is that we can use a variety of inputs like Flume, Kafka, RabbitMQ, ZeroMQ messaging systems, and other inputs, pass this data into the Spark streaming, and we will be passing this data as they arrive, and then we will be getting results that we can store in HDFS, put them into different databases, or put them into different dashboards. Spark stream processing is based on taking the input data, passing them through the Spark streaming, and that functionality is going to create small batches of input for the Spark engine that will then produce the result that consists of batches of processed data. The processing of micro batches of data collected over interval of time is the mode how the Spark deals with streaming. The model is unifying batch, interactive, and streaming models, and internally it is using something called the dstream, which is a sequence of resilient distributed datasets representing a stream of data. Flink streaming is a true streaming system. It has adjustable latency and throughput, and it has a very rich functional API. What is interesting in this API is that it has a strong windowing semantics. We can define policy-based flexible windowing, which is based on things like time, count of elements, deltas. We can provide with various temporal operators. And we have also various settings for fault tolerance. At least once is the one that is currently implemented, and the goal is to provide functionality for exactly once. Both Spark and Flink streaming provide very exciting alternatives to the so far existing stream processing systems. And one particularly interesting thing is the integration that they enable in the area of combining stream with batch processing, which we'll see in the next section. In this section, we will introduce the Lambda architecture. Lambda architecture is providing a solution to the problem of combining a real-time with batch data. Here is how Lambda architecture works. On the left-hand side, we have incoming data. This set of incoming data is going to be split. It is going to be fed to the upper part, which we call the event layer or a speed layer. And this is where we will typically use our stream processing architecture, and we will be processing real-time data. The data is being processed in real time, and we are creating a view on what we can calculate based on a relatively small fragment of real-time data. In the lower part of this diagram, we see that the data is coming in, and it is typically appended to the master dataset that we have for the batch layer. That can be, for example, done by appending the data in the HDFS. Periodically, we are going to run our batch update. For example, we can run Hadoop MapReduce, and based on the master dataset that includes a large volume of data and all of our historical data, we are going to create a view. We call this a batch view, and we are going to place it into the serving layer. What we do in this area is to create some rolling values that we will then combine with what we see as the real-time update. So we will merge the results of our batch processing with the real-time insight. And typically, we will be storing that into some database that will be used for reading from our applications. And we are going to run the queries on this database, which is then going to provide us a combined insight of the batch processing and of the real-time data stream. For example, HBase could be a good store for that purpose, but we have also some specialized stored for these tasks. A Lambda architecture provides us with the combined solution so we can process real-time and batch data together. This is a big advantage of the Lambda architecture. However, there are some problems. One of the problems in implementing Lambda architecture is that we have a functionality that exists in the event layer, and the similar functionality exists in the batch layer. If you are using systems like Storm and Hadoop, you will need to use two different programming environments to implement your jobs. Once as a streaming job, the second time as a MapReduce job. And that is cumbersome and requires duplication of effort. A newer programming system as Apache Spark and Apache Flink would enable us to have the same or very similar code for both layers, and that would significantly improve the productivity in implementing the Lambda architecture. In this section, we will talk about introducing Big Data and NoSQL in the enterprise. One of the common questions that we get is, what should we do if we are a relational database practitioner? Which path would be the most optimal for us? I would always recommend going for a quick win. And that means typically starting with Hadoop and Hive or Pig. Hive is a good starting point if you have experience with relational databases. The fact that Hive is based on SQL is going to make it easier to move towards Hadoop and big data. Many users later switch to Pig when they are dealing with more complex programs. The ability of Pig to be incrementally developed line by line, trying it out, developing program in little pieces is very beneficial. Both approaches would be beneficial for you if you are a data professional because both of the approaches avoid Java programming. Now, if you're looking for more power, I would recommend looking into Scalding. Scalding is a Scala domain-specific language which enables for very effective programming of Hadoop MapReduce jobs. It provides the paradigm which is very appealing because the MapReduce programs will look like ordinary programs that are operating on in-memory data collections. Spark and Apache Flink would have the similar approach. Implementing data warehouse and ETL with Hadoop would be another very good choice. Even if you don't have huge amounts of data, using Hadoop in this role could be a very interesting choice. We are often using the definition of big data, bigger than you are used to. And Hadoop warehouse or ETL implementation can be very interesting because it can free your existing relational databases to do other tasks, and you can also see significant reduction in cost. Now, you will find applications where Hadoop batch processing is not a good match. Then what you should do is to check various NoSQL databases. Perhaps Apache Cassandra could be a good choice for you, or MongoDB, or one of the many players in that field. Using Hadoop as ETL is not an overly glamorous approach to big data, but it is very pragmatic, it is easy to start with, but it ends up often messy in practice. We need to deal with a variety of features like data integration, workflow, process orchestration, and scheduling, and the tooling that we have on the Hadoop side is not as sophisticated and mature as what we find in conventional relational systems. One of the attractive points when you are dealing with large volumes of data is that Hadoop can give you cheaper and faster processing than a relational database. And the dealing with simple ETL is often a quick win for Hadoop and a great way to gain experience and introduce Hadoop in a cost-effective way in the organization. You should remember that the tooling is not as fancy as you may have learned to expect from relational stores. One thing that you should always do in these systems is to integrate with existing applications. And for that, you will start with Scoop. Scoop will integrate relational databases and Hadoop in both directions. And the other system that you should look into is Flink. It is organized around the concepts of sources, pipes, and sinks. It provides us with transactional transport of data and has a very rich collection of adapters that can move log files, that can enable us to periodically read such data, integration with messaging systems, services, and even social media. One thing to consider is that you could deploy big data in the cloud, and that can be your private or a public cloud. In a conventional environment, when you need increase in performance, you would go and buy new hardware. The problem is that in many cases, we need to handle just a peak, and in that case, our infrastructure is going to be underused. On the other hand, if we are handling bursts, we cannot respond on such a short notice, go and get all the hardware that we need. This is why cloud is so interesting. When our needs increase, we can dynamically allocate only what is needed, and then when we are done with our computation, we can release the resources. We can process various bursts in our requests without buying new infrastructure. And also, we can provide for redundancy across multiple data centers. In that case, we may buy just enough infrastructure for normal loads, and we can be doing a cloud bursting where we go and move the processing temporarily to the cloud. So when we are dealing with cloud processing and big data, we can run and administer our own Hadoop cluster, or you could use pre-configured Hadoop system in the cloud. You have various options, and depending on how sensitive are you to having data in the cloud, you can choose to run this either in your private or in a public cloud. One thing you should not forget is that in every enterprise, your processing needs will not end just by running Hadoop. You will be working in a workflow in which you will be acquiring data that will come from various sources. The data may come in different formats. It can come with different velocity. And you first need to store this data. You need to analyze what is in this data. This is where we would be using our Hadoop MapReduce programs. The results of our computations would often need to be visualized so they can be consumed. We also need to manage both our data and big data programs. We need to share the data, and here we are dealing with some tricky issues because movement of data in petabyte scale is very cumbersome. And we should not forget integration with existing systems. Our enterprises need to derive value from both operational and big data systems. And as you are working on such applications, the appetite of your organization will grow and you will be starting the next cycle of development. One of the critical things in working with big data is to provide business value from the big data chain. You need to provide tangible results. You need to execute in time and cost-effective manner. There are organizations that get seduced by the big data systems and they start playing and experimenting and never provide anything tangible to the business. You should work with the business in order to figure out what pain point can you solve with big data and NoSQL technologies. In this video, we will introduce the concept of polyglot persistence. Imagine that you are dealing with a business application, for example, some application in e-commerce, and we need to choose a database for different parts of our application. In our application, we are dealing with session data. The session data is coming from web applications that keep track of interactions of user with the web application. Then we have various logs. We have price updates, and we would like to keep track of those and monitor them in real time. We have product information. Our products come with a variety of descriptions, depending on our vendors, and some of them would have very different organization than the others. Then we have a system that is dealing with customer-agent relationships. Customers and agents can enter in a variety of relationships, and we may also have to deal with distributors and manufacturers, and one entity can play various roles. Then there is the price and operational analytics. They will be dealing with large volumes of data. We also have a transactional data from our e-commerce systems. And now when we look into all of this, the question is, what database would be the best choice for our application? Well, it turns out that not a single database is going to be best for everything. And this is why we will use different databases for different functionality. Now, what we will show here is an extreme case in which we are choosing one database for each of the areas of our application. First, for session data, we can store our data in a key value store. The key can be the user ID, and the value would be the content of the user session. In dealing with logs, particularly when the values are coming with great speed, Columnar Stores would be very useful for that. We can also organize our data so that we have product and every price update can be done or stored in a separate column with the timestamp as the name of the column. Product information that can vary in its format can be best stored in a document database. Customer-agent relationships will benefit from being stored in a graph database where we can explore the relationships between different parts. Dealing with large volumes of data, as in price and operational analytics, can be achieved with Hadoop and conventional MapReduce and batch jobs. And finally, for the transactional data, we have a place for our old friend relational database. The fact that we have a big data and NoSQL stores does not mean that the relational database does not have its place. Typically, relational database is the best system for dealing with transactions. Polyglot persistence is when we use a variety of database stores in one application. Notice that in this organization, for our particular application, we are using 6 different databases. Technologically, that can be an optimal choice. But organizationally, you will have now 6 different headaches. For each of these systems, you need to be able to find somebody who is familiar with the technology, somebody who will be able to administer, configure, and fine-tune the systems. And normally you would go with that many different stores only when you're pushing your systems to their extreme capabilities. Normally, for a smaller system, perhaps you could consider a relational database that can handle all of this to some extent. So normally you would try to minimize the variety of these databases and make your operations easier. But you know that if you are pushed to the limits of the technologies, you could go into true polyglot persistence and have a variety of stores deployed. Now, a software engineering aspect is that you would like to reduce coupling from a particular data store in your application. In this diagram, we have two parts in our application. We have a client package and we have a product data access object. Product data access object is going to be a software component that is encapsulating access to the database. So let's say for our products, we are using MongoDB, but at some point, for a variety of reasons, we may decide to switch to Cassandra, or vice versa. We would not like that the details of the database propagate throughout the whole application, and we would like to be able to localize the changes just to one narrow area of the product data access object. This is using one of the standard design patterns for enterprise computing. In design for polyglot persistence, we recommend that you think about change and design for change, but do not overcomplicate. One of the interesting areas of exposing database functionality is working with NoSQL, REST, and cloud applications. So these technologies, REST and cloud, would provide a great way for separating data from particular technologies. Usually we are using REST for communication, and some databases already come with service APIs, and there are many APIs that have been developed by the community. Also, a new thing is a database as a service cloud offering. So you don't need to install anything. Data Store is exposing its API and it is available in a cloud. So you only need to send data to the system like this. In this video, we will introduce the 7 habits of successful big data and NoSQL projects in the enterprise. First, actively look for solutions where the big data and NoSQL can ease the pain. Do something useful for business. The business may not be aware that you will be playing with these cool technologies, and you need to look how can you help the business with your big data and NoSQL systems. Make sure you deliver tangible value to clients. The reason we are advising that is because in many organizations, technologists start playing with the technology and they forget about delivering tangible results to clients. After you get your first applications to work, create a NoSQL big data introduction and governance plan. If you don't introduce governance, big data and NoSQL systems tend to be more difficult to manage than conventional relational stores. Relational stores have a well-defined schema, which we can inspect. For many NoSQL and big data systems, the schema is actually only present in code of the application. We call that schema on read. And you need to govern your application development so that you keep track and have a clear descriptions of the data that you are operating on. On the other hand, there are organizations that start doing a very heavy governance first, and they may spend a couple of years planning their adoptions of big data without having a single system deployed. Prioritize. Always look what are the most useful things for the business. Try to implement them first, and then you play and experiment with cool features of your new technologies. You must always integrate with existing IT. One of the easy ways is to start applying NoSQL and big data for simple tasks, maybe some ETL. Replace an existing functionality with the big data part of functionality and integrate with existing systems. Make sure you hire or grow your big data and NoSQL champions. These are new technologies. Many of the skills of relational developers do not apply in this setting. We all need to acknowledge that we don't know everything and that we need to learn about these new techniques and systems. Identify your champions and grow them. Finally, this is a new field. We see that speed of development of new systems and technologies is really breathtaking, and you should be always on the lookout for the new tools and technologies, because often in this space, a difference of 6 months can introduce significant improvements in the products. Congratulations! We are done with the course. At this point, you have a broad overview of various big data and NoSQL systems. Now you're ready to go deeper. Check out the other titles in the O'Reilly portfolio and start doing and learning. Thank you.